The dark is older than you think. It was here before the first mammal blinked its cautious eyes in the Paleocene dawn. It was here before the last Triceratops folded its enormous body against the cooling earth of a late Cretaceous evening, its frill pale in the fading light, its slow breath rising like smoke into the still air. The dark was here before all of that, stretching back through time in a silence so deep it has no name in any human language. You're lying inside that dark right now. The same dark that covered the Mesozoic world, the same dark that fell over the Permian seas, the same ancient absence of light that has cradled every sleeping creature since life first developed something like sleep. You are not alone in this darkness. You're simply the latest creature to close your eyes inside it. Let that thought settle over you like a slow tide. You are part of something immeasurably old. The body that is resting now, the breath that is slowing, the mind that is beginning to soften at its edges, all of this is continuous with something that has been happening for hundreds of millions of years. Other animals have done exactly this. They have breathed slowly in the dark. They have let their muscles release. They have let the world continue without their attention for a few hours, trusting that it would still be there in the morning. Tonight, the story you will drift through is one of ancient secrets. Things that lived in the deep past that were stranger, more beautiful, more haunting than any story we could invent. The dinosaurs did not belong to the world we imagined for them. They were more complicated than the skeletons in museums, more textured than the paintings on children's bedroom walls, more present than the reconstructions in films. They had colours we can now name. They had sounds that no human ear ever heard. They had behaviours that would take your breath away with their tenderness or their strangeness or their sheer improbable scale. These are not frightening stories. They are wonder stories. They are the stories of a world that existed for so long and changed so slowly and held so many forms of life that simply sitting with the knowledge of it is enough to make every human worry feel briefly, gently, small. Lie back. Let the weight of the day fall away from your shoulders, your arms, your legs. The night is around you. The dark is older than anything that troubles you. And the story begins a very long time ago. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this every week, and there will always be another world waiting for you when you return. Imagine standing inside the Natural History Museum in London at 3 a.m, not as a trespasser, not with any urgency, but simply as a presence allowed to be there while the building is empty, and the cleaning staff have gone home, and the security guard is somewhere distant behind a door watching a screen. The great central hall is dim, the skylights above let in a pale wash of London night, grey and diffuse, the colour of fog held up against a candle. The dinosaur skeletons stand in this light as they always stand, patient, enormous, indifferent. You walk slowly between them. The sound of your footsteps is absorbed by the high stone ceiling. The Diplodocus skeleton, or rather the cast of a skeleton since the bones themselves are safely stored, arches its long neck toward you with the mild curiosity of an animal that died 90 million years before curiosity was ever named. Its rib cage is a cathedral of bone. Its legs, which in life would have carried 70 tons of flesh and breath and appetite, stand on their marble platform as quiet as furniture. Here is the first secret of the bones. For most of the history of paleontology, for the better part of 2 centuries of digging and describing and interpreting, nearly everything we thought we knew about what dinosaurs actually looked like was wrong. Not wrong in the way that early maps were wrong, slightly off at the edges. Wrong in the way that a shadow is wrong about the object that casts it. The skeletons were real. The bones were genuine. But between the bone and the living animal stretched a distance that science had been underestimating since the very beginning. Consider the skin. Fossilized skin impressions have been found for dozens of dinosaur species. Hadrosaurs, sauropods, certain theropods. These impressions tell us something. They tell us about texture, scales or bumps, or in feathered species the negative space where feathers once attached. But they tell us almost nothing about colour. For nearly 2 centuries, the colour of every dinosaur illustration was essentially invented. Green, because reptiles are sometimes green. Brown, because large land animals are often brown. Grey, because elephant skin is grey and Triceratops was large. These were guesses dressed as convention, and convention eventually becomes belief. The truth is stranger, and the truth began to emerge from the smallest possible source, melanosomes. Melanosomes are the microscopic sausage-shaped structures inside cells that produce pigment. In living animals, the shape of a melanosome can tell you what colour it produces. Spherical melanosomes tend to produce reddish-brown pigments. Elongated ones produce black or dark grey. In 2010, a team of scientists examined exceptionally preserved feathered dinosaur fossils from the Yixian Formation in northeastern China. Fossils so detailed that the impressions of individual feather barbules had been preserved in the fine-grained stone, and inside those impressions they found melanosomes. Not the animals themselves, not living tissue, but the microscopic architecture of pigment production, frozen in rock for 120 million years. The dinosaur they examined first was Anchiornis huxley, a small, four-winged theropod about the size of a crow. The melanosomes in its fossils told a story in colour that no artist had imagined. Its body was predominantly black and white, its legs were speckled, its face bore a reddish-orange crest of feathers, like the crest of a woodpecker, not grey, not green, not the muddy khaki of every dinosaur book your childhood ever placed in your hands. Black and white and red, as precise as a bird in a field guide, as individual as a living creature. Lie with that for a moment. 120 million years ago, a creature the size of a crow moved through a warm Chinese forest in colours we can name. It had a reddish crown and black wings and white speckles on its legs. If you had seen it, you would have recognised it the way you recognise a woodpecker or a magpie, as something with visual identity, something that claimed a particular corner of the visible world. It was not anonymous, it was not grey, it was specific. Microraptor guy, another feathered dinosaur from the same period, yielded melanosomes of a different kind. These were the elongated, organelle-like structures associated with iridescent black pigmentation. In living birds, this pattern produces the glossy, shifting darkness of a crow's wing. Not simply black, but black that contains colour, that moves between blue and green and purple depending on how the light strikes it. Microraptor had those feathers. A small, gliding dinosaur of the early Cretaceous moved through its forest in iridescent black, like a raven cast back through time, its feathers catching the Mesozoic sun in the same shifting colours that crows still carry today. You breathe slowly in the dark of the museum. The bones around you are the same bones they have always been. But they are different now. They are not placeholders for grey imaginary animals. They are the scaffolding of specific creatures, creatures with colours and with faces that were individual in the way that living faces are individual. Somewhere in the mineralised matrix of these fossils is information that we are only beginning to learn to read. The face is perhaps the most arresting example. For most of modern paleontology, the faces of large theropods, including Tyrannosaurus rex, were reconstructed with the teeth always visible, the lips perpetually pulled back in the grinning exposure that became iconic. The museum skeletons show this, the film versions show this, the children's toys show this. A Tyrannosaurus without visible teeth is practically unimaginable. But in 2023, a detailed study comparing the tooth-to-jaw proportions of T-Rex with those of modern reptiles concluded that large theropods almost certainly had lips. Not the thin, mobile lips of mammals, but fleshy coverings similar to those of monitor lizards and other large-toothed reptiles. Coverings that would have held the teeth inside the closed mouth, keeping them moist, preventing them from drying and weakening. A T-Rex with lips would have looked, at rest, more like a very large, very dangerous lizard than like the perpetual snarl creature of popular imagination. The teeth would have been hidden when the mouth was closed. The face would have been smoother, more complete, less skeletal. This is, in a way, more unsettling than the version we invented. The invented version is at least recognisably monstrous. The corrected version is monstrous in a different way. It is almost normal. It is the face of something that could be described without recourse to horror. The face of something that had, in its own terms, a face. The thing we feared turned out to have been, all along, more like a face than we were comfortable with. The bones in this museum have been standing here for over a century. Millions of people have walked between them. Children have pressed their noses against the barriers and looked up at the arch of ancient ribs. All of that time, the bones were holding their secrets in plain sight, waiting for the questions that would eventually slowly begin to reveal the truth. The museum is quiet around you now. The skylights are beginning to grey with the earliest suggestion of approaching dawn somewhere far off across the city, still hours away. The Diplodocus arches its neck in the dim light, patient, enormous, unknowable in its completeness, and yet more known than it has ever been. You are learning to see something that was always there. The darkness inside the bones is slowly, gently, becoming light. Let that thought carry you forward, deeper into the ancient world, as your own breathing grows slower and the night settles more completely around you, and the story continues its quiet unfolding through the deep corridors of time. The process of fossilization is itself a kind of story, a story about what happens to a body after life ends, and how, under very specific and relatively rare conditions, something of that body can persist across time that is almost incomprehensible in its length. When an animal dies in most environments, it disappears quickly. Scavengers take the soft tissue, bacteria decompose what the scavengers leave. The bones, exposed on the surface, are weathered by sun and rain and frost, cracked and fragmented and eventually dissolved into the soil. The specific chemistry that allows bones to persist on the surface is limited. In acidic soils, even bone dissolves relatively quickly. In dry alkaline environments, it can last longer, but on the surface, on geological timescales, bone does not last. What allows fossilization is burial. Quick burial, ideally, in sediment that is fine-grained enough to mould around the bones without disturbing them, wet enough to exclude the oxygen that bacterial decomposition requires, and chemically appropriate for the mineralization process that transforms organic bone into rock. Riverbanks and lake beds and shallow seafloors are ideal. Volcanic ash deposits can preserve extraordinary detail. Even ancient tree resin, amber, can preserve the soft bodies of small organisms in three-dimensional detail, a different kind of fossilization that requires no mineralization at all. The mineralization process, when it occurs, is gradual. Water percolating through the sediment carries dissolved minerals, silica, calcium carbonate, iron compounds, that gradually replace the original bone matrix, atom by atom over thousands of years. The process is not replacement in the sense of one substance being removed and another deposited in bulk. It is an exchange at the molecular level, the organic molecules of the bone being displaced by inorganic mineral molecules as the surrounding chemistry slowly changes the composition of the structure. This is why fossilized bone is so much heavier than fresh bone. Fresh bone is about 30% organic material, collagen and other proteins, and 70% inorganic mineral, primarily hydroxyapatite, a calcium phosphate compound. In a well-mineralized fossil, the organic fraction has been almost entirely replaced, and the density increases accordingly. What you hold in your hands when you hold a fossil is almost entirely mineral, a rock in the precise shape of something that was once alive. Almost entirely, because as Mary Schweitzer's work demonstrated, the almost matters. Under certain preservation conditions, fragments of organic material can persist, not intact, not functional, but present. The collagen fragments extracted from Brachylophosaurus bone, the hemoglobin-associated structures in T-Rex femur. These survivals are not the rule, they are the remarkable exception, but their existence reminds us that the boundary between the organic and the mineral is not as absolute as it seemed, and that the information preserved in fossil bone is not limited to shape and size. In the Natural History Museum in London, in the collections that are not on public display, the vast storage areas that hold far more specimens than could ever be exhibited, there are drawers and shelves of small fossils, fragments, isolated bones, partial skulls, scraps of teeth. Each one is labelled with its species identification, its location of discovery, its geological age. Each one is the remains of a specific animal that lived at a specific time in a specific place and died and was buried and was mineralized over millions of years and was eventually found by a human being and brought here. The collections at the Natural History Museum contain over 80 million specimens across all branches of natural history. Of those, the paleontological collections include tens of thousands of dinosaur specimens. Most of them are not large, spectacular skulls or complete skeletons. Most of them are the small, unglamorous fragments that constitute the bulk of the fossil record, the isolated teeth, the fragmentary vertebrae, the partial limb bones that allow identification and measurement but do not photograph well and do not appear in popular books. These fragments are the real foundation of paleontology. The complete skeletons are the compelling display pieces, the things that populate museums and capture public imagination. But the isolated teeth, found in their hundreds and thousands across the Mesozoic rock formations of the world, are what allow the construction of a genuine picture of Mesozoic diversity. A tooth can tell you a great deal. The diet of its owner, its approximate size, its position in the ecosystem, its evolutionary relationships. A tooth is a small thing, but it is a precise thing shaped by millions of years of natural selection for the specific task of processing the specific food that its owner required. In the dim maintenance lighting of the museum's storage areas, the fragments are quiet in their drawers. Each one arrived here from somewhere, from a quarry face in Montana, from a riverbed in Argentina, from a desert outcrop in the Gobi. Each one completed its long migration from the Cretaceous, through the rock, through the erosion that brought it to the surface, through the hands of the paleontologist who recognized it and collected it, through the preparation laboratory where the surrounding matrix was painstakingly removed, and finally to this drawer, this label, this silence. The museum is quiet at 3 a.m. The Diplodocus stands in the entry hall with the same patient indifference it has maintained for over a century. The collections sleep in their drawers, and somewhere in the amber collections, suspended in Cretaceous tree resin for 100 million years, a small insect preserves in perfect three-dimensional detail the specific moment of its entombment, a moment as specific and as particular as any moment that has ever been lived, preserved against all reasonable expectation in a bead of ancient gold. Let the museum hold its quiet around you. Let the weight of its collections, 80 million specimens, 80 million lives compressed into mineral and preserved in drawers and cases and trays, be a kind of company in the dark. All those lives patiently present, all those forms waiting to be understood more completely than they have been understood yet. The dark of the museum is very old. The dark you are resting in is part of the same dark. The specific weight of a fossil depends on what replaced the original bone. Silicification, replacement by silica, the mineral that makes up quartz and chert, produces the densest fossils, hard and almost glassy when cut and polished. Calcification, replacement by calcium carbonate, produces fossils that are slightly less dense but still far heavier than fresh bone. Pyritization, replacement by iron sulfide, which produces the gold-coloured mineral pyrite, creates fossils with a distinctive metallic luster, often preserved in extraordinary detail but prone to slow oxidation when exposed to air, the pyrite eventually breaking down into sulfuric acid and iron oxides that can, over decades, destroy the specimen. The preparation of a fossil, the painstaking removal of the surrounding rock matrix to expose the bone, is one of the most skilled and labour-intensive activities in paleontology. The tools range from pneumatic chisels for bulk removal to dental picks and fine needles for detail work to air scribes for the finer surface preparation. Chemical preparation using acids is used in some cases, particularly for small specimens in limestone matrix, where the calcium carbonate of the surrounding rock can be dissolved away while leaving the silicified or phosphatized fossil intact. The time required for major preparation projects is staggering. The preparation of a complete T-Rex can take 30,000 hours of skilled work. The Tyrannosaurus named Sue required over 25,000 hours of preparation before she was ready for exhibition. The preparation of a complete sauropod skeleton, the bones often partially crushed, the matrix often intractable, the individual elements numbering in the hundreds, can represent decades of part-time work spread across multiple preparators. This labour is not performed for money in most cases. The scientists and volunteers who prepare fossils are doing it because the information contained in the fossil is worth the effort, because the specific reality of a specific animal, locked inside a rock for millions of years, is worth the enormous expenditure of human time and skill required to extract it. The motivation is the same motivation that drives all scientific inquiry, the conviction that the world is knowable, that the knowledge is worth having, and that the work of acquiring it is a worthwhile way to spend a human life. The preparator in the laboratory, working under magnification on a fragment of Cretaceous skull with a needle the diameter of a human hair, is doing something that connects directly to the animal that produced the skull 75 million years ago. The animal lived. It died. Its bones were preserved by a specific set of geological accidents. They were found by a specific person on a specific day. They were brought to this laboratory. And now a human being is removing, grain by grain, the matrix that has covered them for millions of years, gradually revealing a surface that has not been exposed to air since the Cretaceous. The moment when a new surface is revealed in preparation, when the needle lifts a fragment of matrix and the bone appears beneath it, its texture and colour specific and clear, is described by experienced preparators as having a particular quality unlike any other experience in the science. Not the dramatic quality of a film, not a sudden revelation, but something quieter and more specific. The recognition that you are looking at something that has been unseen for an inconceivable length of time, and that your eyes are the first eyes to rest on this specific surface since the animal was alive. The T-Rex femur that Schweitzer studied, the one that yielded the flexible blood vessels and the round structures that might have been red blood cells, was prepared in a laboratory in Montana in the 1990s. The specific surface that was exposed during preparation had not been exposed to air since the Cretaceous. The organic material preserved inside the bone, the fragments of collagen, the iron-bound hemoglobin derivatives, had been sealed inside the mineral matrix since the bone was buried in the late Cretaceous river sediment. When Schweitzer dissolved a fragment of that bone in mild acid and saw the flexible, translucent tubes emerge from the dissolving mineral, she was the first person in the history of the world to see what was inside a T-Rex bone. Not a reconstruction, not a model. The actual interior of an actual bone from an actual animal that had walked in Montana 68 million years ago. That moment is the apex of what paleontology is. The long chain of events, the animal's life, its death, the geological accident of its burial, the mineralization over millions of years, the erosion that brought it to the surface, the discovery, the preparation, the analysis, all of it leading to a single moment of genuine contact with the deep past. The transparent tube in the acid solution, flexible and real, a structure that existed inside the body of a living Tyrannosaurus. The museum is quiet around you. The bones stand in their patient arrangements, and somewhere in the collections behind the public galleries, in acid-resistant containers in temperature-controlled rooms, the molecular residue of the Cretaceous is preserved in what remains of ancient protein, waiting for the next question, waiting for the technique that does not yet exist but will eventually be developed by someone who finds the waiting worthwhile. The patience of science and the patience of the geological record are a matched pair. The record waits in the rock, the science waits in the human impulse to know. And between them, very slowly, over centuries of accumulating inquiry, the distance is closing. Let that slow closing be a kind of comfort. Things are being understood that were not understood before. The world is becoming more knowable, not less. The Cretaceous is coming closer. The dark inside the bones is very gradually becoming light. The relationship between paleontology and public imagination is unlike the relationship between any other science and the people who are not professional practitioners of it. Astronomy produces wonder, but the objects are unreachably distant. Physics produces wonder, but the mechanisms are abstract. Paleontology produces wonder that is embedded in physical objects that can be touched, in landscapes that can be walked through, in museums where the bones themselves are present in the room. The child who stands in front of the Diplodocus and tilts her head back to see where the neck ends is not engaging with an abstraction. She's in the physical presence of something that was alive, that breathed, that had a heartbeat, that looked out on a Jurassic world from those same eye sockets. The bones are real, the scale is real, the wonder is earned by reality, not invented by imagination. This is what makes the study of ancient life so persistently compelling across cultures and generations. Not the spectacle, though the spectacle is undeniable, not the size, though the size is staggering, but the specific factuality of it. These things were real. They lived on this specific planet in a specific version of this specific world. The distance between them and us is enormous, but it is temporal rather than spatial. They were here. We are here. The here is the same here. The geological record is in this sense a form of testimony. Not testimony in the legal sense, not testimony given deliberately or in language, but testimony in the broader sense, evidence left by the world about what the world has been. The bones in the museum are the world's record of itself. the rock's account of what it has held, the compressed residue of lives lived in conditions we can reconstruct but cannot visit. Reading that testimony, the work of paleontology, requires the same basic disposition that any honest reading of testimony requires: patience, attention to detail, willingness to revise understanding when new evidence requires it, and a genuine humility about the limits of what can be known from indirect evidence. The paleontologist cannot ask the T-Rex what it was like. She can only read what the bones say and make the best inference available from that reading. The best inference is always provisional. It is always subject to revision when better evidence arrives. The history of paleontology is a history of revisions, of ideas held confidently and then abandoned as new evidence required new interpretations. The grey lizard dinosaur became the warm-coloured feathered bird relative. The slow, tail-dragging brontosaurus became the upright, actively moving apatosaurus. The cold-blooded ectotherm became the mesotherm, or possibly in some lineages the true endotherm. Each revision moved the picture closer to the truth. The picture is not complete. It will never be complete because the fossil record is always incomplete and the past is always partly inaccessible. But it is richer than it was, and it is moving in the direction of richer still. Somewhere in that direction is the actual reality of what the Cretaceous world was like. Not our current best reconstruction, but the thing itself. The warm afternoons and the low calls of large theropods and the iridescent feathers of small predators and the deep slow breathing of the titanosaur herds. We cannot reach it directly. We can only approach it asymptotically through the accumulation of evidence and the improvement of technique. The approaching is itself valuable. The direction of approach is towards something real, something that was as real as this room, as real as this night, as real as the specific weight of a fossil vertebra in an open palm. The dark inside the bones is very gradually becoming light. Let that gradual illumination be the thought that carries you into the deeper dark of sleep. The world is knowable. It is becoming more known. You're part of a species that is slowly and imperfectly and with many wrong turns, learning to read the world's account of itself. That is a good thing to be part of. Rest in it. Close your eyes more completely. Let the world behind your eyelids become not the darkness of a room, but the darkness of 75 million years ago, and let the first thing you notice be not what you see, but what you hear. The first sound is wind, not the wind of today, not the wind that moves through the particular trees and across the particular landscape outside, whatever window is nearest to you right now. This is Cretaceous wind, moving through a world of different proportions. The forests of the late Cretaceous were dominated not by the broadleaf deciduous trees that cover most of the temperate world today, but by conifers, enormous, columnar, with bark that was rough and fragrant with resin. Their needles moved differently in the wind than broadleaves do. They hissed rather than rustled. They produced a higher, more continuous sound, like white noise filtered through the memory of rain. Beneath the conifers, in the undergrowth, the first flowering plants were still relatively new, having appeared only in the early Cretaceous, and still finding their place in a world that had been conifer-dominated for over 100 million years. Magnolias and their relatives bloomed in clearings, their large white flowers catching the slant of late afternoon light. Ferns covered the forest floor in dense mats, their fronds catching and holding moisture, their surfaces the particular deep green of things that have been green since before anything with eyes existed to see green. Listen past the wind, there are insects, always insects. They are the auditory baseline of every terrestrial ecosystem that has existed since the Carboniferous. The late Cretaceous had crickets, or the early forms of what would become crickets, and their stridulation, the sound produced by wing against wing, leg against body, was essentially the same sound that crickets make tonight wherever you are. Some sounds are so perfectly engineered that they require no modification across hundreds of millions of years. The cricket's song is one of them. If you have ever lain in summer grass and listened to crickets, you have heard something nearly identical to the sound that played beneath the footsteps of dinosaurs. There were beetles in the bark of the conifers, and the sound of their industry, small, dry, persistent, was part of the texture of the forest. There were primitive flies and the ancestors of modern bees moving between the new flowers, and their wings produced the same low-frequency hum that flower-visiting insects produce today. The acoustic world of the Cretaceous was in many ways more familiar than its visual world. You could close your eyes in that forest and hear something recognizable. It is only when you opened them that the strangeness would arrive. And now, from somewhere in the middle distance, a sound unlike anything in the world you know. It is low, very low. Below the range of easy hearing, somewhere in the infrasonic register, where sound becomes sensation as much as perception, where you feel it in the chest as much as you process it in the ear. It comes in slow, rhythmic pulses, not a continuous tone but a series of deep, resonant exhalations, like the call of a bittern heard across still water, amplified to a scale that makes the bittern seem like a draught of sound rather than a full expression of it. This is, in all probability, what a large theropod dinosaur actually sounded like. The iconic roar of the Tyrannosaurus rex, the sound that has defined the creature in film and imagination for 30 years, is, by the best current scientific understanding, fiction. Not fiction in the sense of being carelessly invented, but fiction in the sense of being a plausible-sounding impossibility. Birds are the living descendants of theropod dinosaurs, and birds do not have the larynx structure required to produce the kind of open-mouthed roar that films have given their ancient relatives. What birds have is a syrinx, a vocal organ unique to birds, located deeper in the respiratory system. And what large birds tend to produce are not roars but booms, resonant calls made with the beak closed or nearly closed, calls that travel through the body as much as through the air. The cassowary of the Australian rainforest produces a call at frequencies as low as 23 Hz, at the very edge of human hearing, where sound becomes a pressure rather than a pitch. The ostrich makes a deep ventral boom during courtship that can be heard from a kilometre away. The emu produces sounds so low that they were not fully catalogued until infrasound recording equipment became available. All of these birds are ratites, large, flightless birds often considered among the most archaic of living bird lineages. Their calls may offer the closest acoustic model we have for what large dinosaurs sounded like. The Tyrannosaurus rex, by this model, probably sounded something like a very large, very slow pigeon. Not the gentle cooing of a city bird, but the deepened, resonant version of that sound, slowed and amplified to a register that would be felt in the sternum before it was heard by the ear. A sound that might travel miles through a Cretaceous forest, carrying information, territory, identity, reproductive state, through the dense air of a warm world. There is something wonderful and something faintly comic about this, and something that settles, once you sit with it, into a kind of rightness. The most feared creature in the history of land-based predation made a sound like a very large dove. The world was not what we imagined. It was weirder and quieter and somehow more intimate. Now add other sounds to the Cretaceous night. The pterosaurs are calling from their roosts in the high branches of the tallest conifers. Pterosaurs, which were not dinosaurs, but were the flying reptiles that shared the Mesozoic world with them, had complex bony crests on many species, and recent research suggests these crests may have functioned as resonating chambers, amplifying vocalizations the way the hollow body of a guitar amplifies a plucked string. The calls of crested pterosaurs would have been haunting, low-frequency sounds with a quality somewhere between a horn and a reed instrument. Not musical in any human sense, but not simply animal noise either. Something in between. Something that would have been unfamiliar to any ear that has ever existed on this planet except those that heard it. Somewhere in the undergrowth a small theropod is moving. Not a large predator, something closer in size to a heron perhaps, or a large turkey. Its footsteps on the forest floor are deliberate, each one placed with the precision of a hunter who knows that sound travels. Its claws curl around fallen conifer cones with a grip that leaves no mark. Its eyes are large and forward-facing, adapted for the specific quality of Cretaceous night. Not total darkness, but the attenuated light of a three-quarter moon filtered through the canopy of an ancient forest. This is Troodon, or a creature like Troodon, a troodontid theropod of the late Cretaceous, notable for having the largest brain relative to body size of any known non-avian dinosaur. It is not large, roughly the size of a human being when standing, but lighter, hollow-boned, built for agility rather than mass. Its brain, proportionally, is not far from that of a modern crow or a raven. Animals that are, as you may already know, among the most cognitively capable creatures alive today. Troodon is hunting tonight. Its prey might be small mammals, the tiny, shrew-like creatures that were beginning to diversify in the Cretaceous undergrowth, mostly nocturnal, mostly tiny, mostly staying very close to the ground and the root systems of trees where larger feet would have difficulty following. Or it might be hunting insects, lizards, the eggs of ground-nesting animals. Its hunting strategy would have resembled a bird of prey more than it resembled the pursuit predation of a wolf or a lion. It would wait, it would track, it would strike with precision rather than force. And here is the thought that the Cretaceous night offers you as you lie still in your own dark. Somewhere in the data preserved in Troodon's skull, in the enlarged optic lobes of its brain endocast, in the forward position of its eyes, in the size of its cerebellum, and the complexity of its olfactory structures, there is evidence of something that might, in a careful and qualified sense, be called experience. Not human experience, not conscious reflection, but experience in the sense of a subjective engagement with the world, a difference, however basic, between the sensation of prey nearby and prey absent, between warmth and cold, between the forest at rest and the forest disturbed. That small, intelligent, large-eyed predator was experiencing the Cretaceous night from the inside. In some form that we cannot fully access or describe, the world existed for it as a world. The darkness was its darkness. The sounds were sounds it recognized. The warmth in the air was warmth that it felt. 66 million years separate that moment from this one. And yet here you are, also in the dark, also in a body that senses warmth and cold, also processing the sounds of the world around you as meaningful rather than random. The distance between that Cretaceous night and this one is immense, but the basic fact of being inside a body that experiences a night, that is not different at all. The Cretaceous wind moves through the ancient conifers. The insects maintain their long continuous chorus. Something large moves slowly through the middle distance, its footsteps felt before they are heard, its low resonant call dissolving into the darkness before it can be fully processed. And the small intelligent hunter in the undergrowth pauses, tilts its head and listens. Just as you are listening now. The night is long. Let it be long. There is nothing required of you but this gentle attention, this slow drift through the oldest dark, this patient company with creatures that lived and breathed and heard the same insects singing, a world away and an eternity ago. The question of dinosaur sleep deserves its own extended attention, because it opens into something that touches the very core of what this night is. We know from the fossil evidence that certain small feathered dinosaurs adopted sleeping postures when they died, or rather, that they died in sleeping postures, which suggests that they were sleeping when they died, overcome by some rapid environmental change. The specimens from the Ixian Formation in China that show this sleeping posture are small troodontids and oviraptorosaurs, their necks curved, their heads tucked toward their bodies in the way that modern birds tuck their heads under their wings when they sleep. The parallel with birds is not coincidental. It reflects a genuine evolutionary continuity. The specific postural preference for sleeping, head tucked, body compact, the core temperature of the head slightly elevated by proximity to the warm body, is a behavior that these small dinosaurs share with their avian descendants. It may go back further still, into the archosaur ancestor common to both birds and crocodilians, since crocodilians also show sleep states, though their sleeping postures are less elaborated. What the brain does during sleep in birds has been studied extensively, and the findings are relevant to any consideration of dinosaur sleep. In birds, sleep consists of distinct stages analogous to the slow-wave sleep and REM sleep of mammals, though the architecture is different. Birds cycle through these stages much more rapidly than mammals, often completing multiple cycles within a single hour. The REM-like phase in birds is characterized by the same features that define REM in mammals: rapid eye movements, motor atonia, temporary paralysis of the voluntary muscles, and elevated brain activity in regions associated with memory processing and learning. The significance of this is that the consolidation of memory in sleep, the process by which the experiences of the waking day are organized, encoded into long-term storage, and integrated with existing knowledge, is not a mammalian invention. It is an archosaur process shared by birds and their dinosaurian ancestors, and probably present in the common ancestor of all amniotes. Memory consolidation in sleep may be as old as complex learning itself. For a Troodon learning the specifics of a new hunting ground, the particular route to the marshy area where small mammals gather, the specific behaviour of prey at a certain time of evening, the identity of rival individuals whose territories border its own, the night would have been the time when these experiences were sorted and stored and integrated. The waking day provided the raw material. The sleeping night did the processing. In this sense, every night that Troodon slept was a night of becoming more knowledgeable, more competent, more specifically itself. The animal that woke in the morning was slightly more capable than the animal that had gone to sleep the night before, because the sleeping brain had done its work. You recognize this process, not consciously. Sleep works below the threshold of awareness, and the consolidation of memory is not an experience you can observe from the inside. But you have felt the results. The problem that seemed insoluble the night before resolves itself in the morning. The skill that was effortful one day becomes easier the next after a night's sleep. The emotional experience that seemed overwhelming in the evening has been processed by morning into something that still has weight but no longer has the sharp edge of the immediate. Sleep is working on you right now. In the most literal, biological sense, the act of resting in the dark is an act of cognitive maintenance. The brain is doing the work that makes you more capable of tomorrow than you are of tonight. You do not need to help it. You do not need to guide it or supervise it or worry about whether it is doing the right things. It has been doing this for hundreds of millions of years. It knows exactly what it is doing. The Cretaceous night is full of sleeping animals, not just Troodon, the small predators, the intelligent ones, the ones we find most interesting because they most resemble us in their cognitive sophistication. All of them. The Edmontosaurus herds, lying down in groups on the riverbanks, their large bodies warm against the cool night air, their flanks rising and falling in the slow rhythm of deep sleep. The Triceratops clusters, their enormous frills dimmed and still, the colour gone now in the sleeping darkness. The ankylosaurs low to the ground, their armoured backs turned to the sky, their short legs tucked beneath them. A whole world sleeping. The most successful fauna that has ever lived on the surface of the Earth, distributed across every continent, filling every available ecological niche, and at night, in the particular hours of the deep Cretaceous dark, all of it resting, all of it allowing its brain and body to do the work that only rest can do. The world is a sleeping world, periodically. Every night the surface of the rotating Earth passes through its own shadow, and the animals on that surface, almost universally, rest. The pattern has been the same since long before the Cretaceous. The night is for sleeping. The body is built to sleep. The brain is built to use that sleep for the most important work it does. You are part of this pattern. You have always been part of this pattern. Right now, in this moment, you are not doing something unusual or optional or escapist. You're doing what the biology of complex animals has always done in the dark. You're sleeping into the future, one consolidated memory at a time. The acoustic world of the Cretaceous had dimensions that we have only begun to explore, and one of the most intriguing involves the question of hearing. Not what the dinosaurs said, but what they could hear. The hearing range of an animal is determined by the structure of its inner ear, specifically the cochlea, the spiral structure filled with fluid and lined with hair cells that converts the mechanical vibrations of sound into electrical signals that the brain can process. The length and structure of the cochlea determines the frequency range that the animal can detect. A longer, more specialized cochlea can detect higher frequencies. A shorter, simpler one is limited to lower frequencies. Crocodilians, as the closest living relatives of dinosaurs alongside birds, have a cochlea that is relatively short and simple, giving them a hearing range concentrated in the lower frequencies. They're good at hearing the low-frequency distress calls of hatchlings, which are among the key stimuli that trigger parental behavior in these ancient animals. Birds have a much longer cochlea and can hear a much wider frequency range, though they generally do not hear as high as mammals. Dinosaur cochlear length can be estimated from endocasts, the impressions of internal skull structures. Studies of theropod dinosaur cochlear endocasts suggest a range of hearing abilities. Small, active, presumably cognitively sophisticated theropods like Velociraptor and Troodon had cochlear proportions more similar to birds than to crocodilians, suggesting a hearing range broader than a crocodilian, potentially extending into the middle frequencies where many important environmental sounds are encoded. Large theropods like Tyrannosaurus had cochlear proportions more similar to crocodilians, suggesting a hearing emphasis in the lower frequencies, consistent with the closed-mouth, low-frequency vocalization hypothesis discussed earlier. The T-Rex may have been exquisitely sensitive to the low-frequency sounds produced by its own calls and by the calls of other large animals in its environment, while being less sensitive to the higher frequency sounds that smaller animals produce. The herbivorous dinosaurs show their own patterns. Hadrosaurs, with their elaborate bony crests, may have been able to hear the specific frequencies that their crest-generated calls were tuned to, creating a communication system in which the sound production and the sound detection were co-evolved. The crest produced sounds in specific frequency ranges, and the hadrosaur cochlea was structured to be most sensitive to exactly those frequencies. The communication system was a closed loop. The caller and the receiver were both adapted to the same channel. This is elegant, and it is paralleled in many modern animals. Frogs and their mates are tuned to each other's calls. Many birds produce calls whose fundamental frequencies match the peak sensitivity of their species' cochlea. The communication system evolves as a unit, the production and the reception changing together, because a call that cannot be heard has no evolutionary value, and a sensitivity to frequencies that no conspecific produces is equally useless. In the late Cretaceous floodplain, the acoustic landscape was structured. Different species were communicating on different channels, different frequency ranges, different temporal patterns, different social contexts. The low-frequency resonance of large theropods on one channel. The mid-frequency complexity of hadrosaur crest calls on another. The higher frequency calls of smaller animals in the undergrowth on yet another. The insect chorus filling the background across the full audible spectrum. A Cretaceous night was not acoustically simple. It was layered, specific, full of information encoded at different scales for different receivers. Every sound in the Cretaceous night was meaningful to some animal. Every silence between sounds was also meaningful. The absence of a familiar call, the gap in the insect chorus that might signal a large animal moving through the undergrowth, the specific quality of a silence that was not peace but alertness. You're hearing the silence of your own room now, not the silence of the Cretaceous. That silence is 66 million years gone, and the specific information it encoded was never meaningful to your ancestors, who were not there to receive it. But your auditory system, evolved from the same archosaur ancestry as the dinosaurs, is still doing what it was always designed to do, monitoring the acoustic environment for information, distinguishing meaningful patterns from background noise, maintaining a low-level awareness of the sounds of the world even as consciousness recedes. The small sounds of the house settling, the distant sound of traffic or wind, or the specific ambient sound of wherever you are. These sounds are being processed by auditory circuits that were laid down in the mammalian lineage over 60 million years of nocturnal life, circuits designed to detect the sounds that mattered to small nocturnal Eocene mammals trying to avoid being eaten in the dark. Your sleeping brain will monitor these sounds all night without your waking. It will dismiss the familiar sounds, the regular settling, the predictable ambient, and remain alert to the unfamiliar, the irregular, the sounds that do not fit the expected pattern of the environment at rest. This monitoring is automatic, ancient, reliable. You do not need to manage it. It will happen whether you attend to it or not. Let it happen. Let the ancient auditory system do its ancient work. The Cretaceous night was full of listening, and your night is continuous with that listening. Every animal that has ever survived a night has survived it partly by listening well. You have inherited that skill. It is running right now in the background, monitoring the acoustic world so that your conscious mind does not need to. The sounds of your room are safe. The ancient monitoring system will tell you if they change in ways that matter. For now, the sounds are familiar, and the familiar is the signal for rest. Let the sounds of the night be what they are. Let them be background. Let them be the specific acoustic texture of a world that is resting around you, as the Cretaceous world rested around the sleeping dinosaurs, the sounds continuing, the information flowing, the night doing what the night has always done. The specific quality of the Cretaceous night, the texture of its darkness, the temperature of its air, the particular composition of its sounds, is not recoverable in its full sensory richness. But we can approach it. We can triangulate from evidence, construct a reasonable facsimile, stand at the edge of the reconstruction and know that we are as close as indirect evidence allows. The temperature of the late Cretaceous night in what is now Montana was probably warmer than a Montana night today. The global average temperature was 8 to 12 degrees Celsius above the current average, and while this did not mean that every region was uniformly warmer by that amount, the distribution of heat was different, with smaller pole-to-equator temperature gradients, meaning the tropics were not dramatically hotter, but the high latitudes were much warmer. It did mean that a late Cretaceous night in Montana was more like a mild summer night than the cold nights that modern Montana is known for. The Cretaceous atmosphere was richer in carbon dioxide. Estimates suggest concentrations 2 to 8 times the current level, which contributed to the greenhouse warming, but also had a subtle effect on the smell of the air. Plants in high carbon dioxide environments often grow faster and produce different proportions of aromatic compounds. The specific smell of a Cretaceous forest, the particular blend of resin from the conifers, the organic compounds from the decomposing organic matter of the forest floor, the specific floral scents of the early angiosperms, the animal smells of a large fauna, was different from any smell available in the modern world. No human nose has ever smelled the Cretaceous. The specific olfactory experience of walking into a late Cretaceous forest is one of the permanently inaccessible things, because smell is not preserved in the geological record. We can know the temperature from isotopic data, the atmospheric composition from proxy records, the plant communities from fossil pollen and leaf impressions, the animal communities from bones and tracks. But the smell, the immediate, intimate, directly sensory experience of the air, is gone. This is a small loss in the context of everything that the geological record preserves, but it is a real loss, and acknowledging it is a way of acknowledging the limits of the knowable. The world is knowable in many dimensions. In some dimensions it is permanently opaque. The sounds are more recoverable, in the inferential sense already explored. The visual world is more recoverable through the melanosome evidence and the anatomical comparisons. The ecological interactions, who ate what, who competed with whom, what roles different animals played in the maintenance of the ecosystem, are increasingly recoverable through isotopic analysis and detailed taphonomic study. But the smell is gone. Perhaps this is appropriate. Smell is the most immediate, most visceral, most memory-linked of the senses. The smell of a particular place can transport you back to a specific memory more directly than any visual or auditory stimulus. If the smell of the Cretaceous were recoverable, it might be too immediate, just too viscerally present, to allow the contemplative distance that the geological perspective requires. The smell would make the Cretaceous too close, too immediate, too present to hold at the specific distance that allows it to be a meditation on deep time rather than a sensory experience. As it is, the Cretaceous is held at exactly the right distance, close enough through bone and track and chemical analysis to be real rather than mythological, far enough through the inaccessibility of its most immediate sensory qualities to remain a subject of imagination as well as knowledge. The balance between the known and the imagined is perhaps exactly right. The imagination fills in what the evidence cannot provide, not freely, constrained by the evidence, shaped by the known facts, disciplined by the understanding that the imagined must be consistent with the knowable, but present, active, contributing the sensory richness that the dry evidence cannot supply. You are imagining the Cretaceous night right now, partly from what has been described in these chapters, the sounds, the visual appearance, the scale, the specific animals and their behaviours, and partly from your own imagination's contribution, the specific quality of warmth you imagine, the specific texture of the air, the specific character of the darkness. That imagined Cretaceous is not wrong. It is incomplete, and it is coloured by your own experience in ways that the actual Cretaceous was not. But it is also, in its way, real, a real imaginative experience, occurring in a real brain, contributing to a real understanding of a world that existed 66 million years before this one. The Cretaceous night and your imagining of it are not the same thing, but they are in contact. The imagination reaches back and the evidence reaches forward, and in the space between them something like knowledge forms. That knowledge is what you're resting in tonight, the long dark of the deep past reconstructed in the medium of a human mind lying in the dark of a specific night in the specific present. Let the reconstruction settle into rest. The evidence is sufficient. The imagination has done its work. The Cretaceous night is as present as it can be from here. And from here it is very present indeed. If you are already beginning to drift, if the edges of the world are softening and the voice is becoming something you follow rather than listen to, then let yourself go. Subscribe so the next story is waiting when you return. Sleep well. 66 million years ago, the world did not know it was ending. This is the first thing to understand about the end of the Cretaceous. The last day before the asteroid was not marked by any particular darkness. The sky was no different from the sky of the day before it, or the week before it, or the century before it. The dinosaurs that moved through the warm Cretaceous landscape of what is now Montana or New Mexico or Patagonia or China had no way of knowing that the specific version of the world they inhabited, the warm, lush, conifer and fern version, the version that had been in some form continuous for over 160 million years, was about to end. They moved through the late afternoon in their usual patterns. Hadrosaurids, the duck-billed dinosaurs, the great herds of the Cretaceous, cropped the low vegetation along riverbanks, moving in groups whose social dynamics we have only begun to understand. Triceratops moved in smaller clusters through the more open landscape, their three-horned faces and enormous frills marking them as individuals even at a distance. Edmontosaurus, the large hadrosaur whose soft tissue preservation has given us more information about dinosaur appearance than almost any other species, moved with the particular unhurried confidence of a large herbivore that, in its own environment, has relatively little to fear from anything that moves slowly enough to be avoided. And somewhere in this landscape, in the late afternoon of 66 million years ago, a Tyrannosaurus rex was resting. Not hunting, resting. This is something that took paleontology a while to accept, that apex predators spend most of their time not hunting. Lions sleep for up to 20 hours a day. Large predatory birds spend long periods perched and motionless, conserving energy. The T-Rex, with a metabolism that we now understand was somewhere between the cold-blooded inactivity of a modern crocodile and the warm-blooded constant activity of a modern bird, was almost certainly a creature that alternated intense activity with long periods of stillness. Imagine it lying down. This is harder than it sounds. Reconstruction of T-Rex posture has been debated for decades, but current understanding suggests that large theropods could and did adopt a more recumbent position for rest. Legs folded beneath the body, the torso lowered, the enormous head resting on or near the ground. Not on its belly like a lizard, the pubic bones would have prevented that, but in a position something like a large bird at rest. The body balanced over the folded lower limbs, the centre of gravity settled and still. In this position, on a warm late Cretaceous afternoon in what will one day be Montana, the largest land predator that has ever lived is breathing slowly. Its lips, we remember now, it has lips, are closed over the rows of teeth that have already taken so many lives. Its eyes are half closed, the nictitating membrane perhaps slightly lowered, filtering the light. The muscles along its neck and flanks, the muscles that give it its characteristic deep-chested silhouette, are relaxed. The thick, slightly rough skin, not scaly like a snake, but textured in the way of large crocodilian skin, with bumps and irregular surfaces, is warm in the afternoon light. It is for this moment simply an animal resting in its world. The asteroid that would end that world was already in the sky. It had been in the sky for some time, not a steady star, but an object approaching with the gradual accumulation of speed that objects gain as they fall toward a gravity well. It was approximately 12 kilometers wide. A rock, a very large rock moving at about 20 kilometers per second relative to the Earth. The flash, when it came, was visible across an entire hemisphere. In a fraction of a second, the energy released was 2 million times greater than the most powerful nuclear weapon ever detonated. The rock did not simply hit the Earth, it was vaporized by the impact, and the vaporized rock and the vaporized crust beneath it became a column of superheated gas and molten material that rose above the atmosphere and fell back as burning debris across the entire planet. Within hours, fires were burning on every continent. Within days, the dust and soot in the upper atmosphere had begun blocking sunlight. But here is how the story continues, and here is why, despite the scale of the catastrophe, this is still ultimately a story of continuation rather than ending. The thin grey line. In rock formations around the world, in Italy, in Denmark, in New Mexico, in New Zealand. There is a visible boundary in the rock record. It is called the KPG boundary, the line between the Cretaceous and the Paleogene. Below it, the fossils of the Cretaceous world. Above it, an absence, and then gradually the different fossils of the recovering world. At this boundary, there is a thin layer of clay, and in that clay there is an anomalous concentration of iridium, an element rare on Earth but common in asteroids. It was the discovery of this iridium layer in 1980 by Luis and Walter Alvarez that first provided strong evidence for the asteroid impact hypothesis. You can visit this boundary. You can go to a roadside outcrop in New Mexico or a quarry face in Denmark, and you can place your finger on a stripe of grey clay, and you can know that your finger is resting on the compressed residue of the worst day in the last 250 million years of Earth history. Below your finger, the Cretaceous. Above it, everything since. The non-avian dinosaurs did not survive what came above that line. Neither did the pterosaurs. Neither did the mosasaurs and plesiosaurs of the warm Cretaceous seas. Neither did approximately 75% of all species on Earth. The extinction was total enough that the very concept of a terrestrial ecosystem had to be rebuilt from whatever survived. What survived, among the animals, was mostly small. Creatures that could live on seeds, on roots, on the detritus of a world without its usual food webs. Small mammals burrowing into the ground. Freshwater turtles and crocodilians, sustained by organic material washing into rivers from the devastated landscape. And birds, the neornithine birds, the lineage that leads to all modern birds, small, ground-dwelling or water-associated, probably eating seeds and insects, passing through the bottleneck of the impact winter as dusty, improbable survivors in a ruined world. From those bird survivors came every bird alive today. Every owl, hunting at night with eyes adapted for near-total darkness. Every hawk, riding thermals above fields in the afternoon light. Every songbird that has ever woken you before dawn, with its territorial declaration. Every hummingbird hovering in a garden. All of them passed through the asteroid, through the darkness, through the long Paleogene recovery, to arrive at the present moment still carrying, in the deep architecture of their cells, the Mesozoic. The carbon in the body of that resting T-Rex became, over the following millennia, part of the soil, part of plants, part of the animals that ate those plants. Nothing is destroyed in the geological sense. Everything becomes something else. The Cretaceous is not gone, it is redistributed. It is still moving through the world in the bodies of the living, in the carbon that cycles through the atmosphere and the oceans, in the chemistry of the rock that underlies every landscape on Earth. And here is the thought that the end of the Cretaceous offers you at the edge of sleep. Everything you are is continuous with something very old. The carbon in your body has been through more transformations than can be counted, through Cretaceous soils and Paleogene seas and Eocene forests and Pleistocene ice, and all the 10,000 years of human agriculture that came after. You're not at the end of a story. You're inside a continuity so long that no human mind can fully hold it. And that continuity is not frightening. It is simply the way things are. Somewhere in a thin grey line of clay exposed in a roadside outcrop, the worst day in 250 million years is preserved as sediment, and above that line the world continued. It always continues. Let that be enough for now. Let the end of the Cretaceous be what it was, not an ending but a hinge, a turning, the world breathing out and then slowly breathing in again. The dark around you is the same dark that fell on the last Cretaceous evening. The stars above whatever roof is above you tonight are the same stars that were above the resting Tyrannosaurus in the warm Montana afternoon, before the sky changed. Everything continues. Everything transforms. Breathe slowly, the night is long and gentle. There is a particular category of fossil that paleontologists call a Lagerstätte, a German word meaning storage place, used in geology to describe a fossil deposit of exceptional quality and quantity. Lagerstätten are rare. They require a specific set of conditions: rapid burial, oxygen-poor environments that prevent bacterial decomposition of soft tissue, fine-grained sediments that preserve detail at scales far below what normal preservation would allow. The Burgess Shale in British Columbia is a Lagerstätte. It preserves Cambrian marine organisms in such detail that the soft anatomy of animals that lived 508 million years ago is recoverable. Not just the hard shells and bones, but the soft parts, the internal organs, the delicate appendages that would normally vanish within days of death. Looking at a Burgess shale specimen is looking directly at Cambrian life with a clarity that should not be possible. The Yixian Formation in northeastern China is a lager state for the early Cretaceous. The fine-grained volcanic ash deposits that characterize it preserve feathers, skin impressions, soft tissue outlines, and even stomach contents in extraordinary detail. This is where the feathered dinosaurs were found, where the melanosome analysis became possible, where our understanding of the diversity and appearance of early birds and bird-like dinosaurs was transformed. The Messel Pit in Germany is a lager state for the Eocene, the period that followed the extinction event. The oil shales of the Messel Pit preserve the post-dinosaur world with the same extraordinary fidelity that the Yixian preserves the dinosaur world. Complete mammals with fur impressions, birds with the original colour patterns visible, insects with the structural colours of their wing scales still intact. The Messel Pit gives us a window into the world of 50 million years ago as clear as a photograph. Each Lagerstätte is a gift, an accident of geological circumstance that preserved, far beyond any reasonable expectation, the specific reality of a specific moment in the history of life. Without these deposits, our understanding of past life would be built almost entirely on teeth and bone, on the durable materials that survive under ordinary conditions. With them, we can see the soft anatomy, the colour, the texture, the fine details of life as it was actually lived. The KPG boundary, the thin grey line, is itself a kind of Lagerstätte, though not in the traditional sense. It does not preserve soft tissue or colour. What it preserves is the signature of an event, the specific geochemical anomaly of the iridium layer, the shocked quartz grains that were produced by the pressure of the impact, the tektites, small glass beads formed from rock vaporized by the impact and refrozen as it fell back through the atmosphere. In some KPG boundary deposits, there is a layer called the boundary clay that preserves the immediate aftermath of the impact in its chemistry. The soot layer above the boundary clay in some sections represents the debris from the global firestorms. Above that, the first recovery flora, the fern spike, a global layer of fern spores that represents the first plants to recolonize the devastated landscape, since ferns are adapted to colonize disturbed ground and can regenerate from underground rhizomes even after catastrophic damage to the above-ground vegetation. The fern spike is, in its way, a message of hope written in rock. Not deliberately, nothing in geology is deliberate, but in the sequence of events it records, there is something that functions like a narrative of resilience. The worst day in 250 million years, the darkness. And then, from the underground, from the parts of plants that survived the darkness, the first green things returning to the surface. The ferns came back before the flowering plants, before the trees, before the complex ecosystems that would eventually produce the Eocene forests and the Miocene grasslands and the world as it is today. The ferns came back first because they are among the most resilient forms of plant life, fast-growing, adaptable, capable of reproducing without flowers or seeds, sustained by underground structures that can survive conditions that would kill the above-ground plant entirely. 66 million years ago, the world was carpeted in ferns, not the decorative ferns of a temperate woodland or the tree ferns of a tropical ravine, but the survivor ferns, the recovery ferns, the ferns of a world that had just been emptied and was refilling itself with whatever had come through the bottleneck. The air above the fern carpet was clearer than it had been for months, the dust settling, the soot precipitating out of the atmosphere. The first light of a recovered day falling on a world that was green again, thinly and tentatively but green. The hadrosaurs were gone, the triceratops were gone, the T-Rex was gone, the pterosaurs were gone, but the ferns were there and the small mammals were there and the birds were there. The small birds, the ground-feeding birds, the birds that had survived the winter on seeds and roots and whatever organic material the devastated landscape could provide. In the morning light of the first recovered day, not the day after the impact but the day after the recovery had reached a point of visible green, the world was different, smaller, quieter. The sounds that had characterized the Cretaceous, the low resonant calls of large theropods, the thud of titanosaur footsteps, the complex social vocalizations of hadrosaur herds, were absent. The loudest animal in the Paleocene landscape was in many regions a bird. But it was a living world. It was a world with morning in it, with the smell of wet soil and growing things, with insects beginning their chorus and birds beginning their own. 66 million years after that morning, the descendants of those birds and those insects and those small mammals have diversified into the full complexity of the modern world. The morning never stopped coming. Your morning will come too. It always does, after the night. The dark is not permanent, it is the necessary other half of the cycle, and the cycle has been cycling reliably since long before any animal existed to experience it. Rest inside the dark, the morning is already on its way. There is a site in New Jersey, a set of fossil beds in the Inverson Marl Pit, that has yielded mosasaur remains, shark teeth, fish bones, and fragments of the animals that lived in the shallow sea that covered the eastern margin of North America in the latest Cretaceous. What makes this site significant for the story of the KPG extinction is its position in the stratigraphic sequence. The fossils from this site span the boundary itself, and the transition from the Cretaceous to the Paleogene is readable in the rock. Below the boundary, mosasaur bones, Cretaceous shark teeth, the fossils of an ocean community that had been in place for millions of years. Above the boundary, an absence. Not a gradual thinning, an absence. The marine community of the Cretaceous is present in the rock one day, metaphorically speaking, and absent the next. The iridium layer is there, a thin chemical signature of the asteroid, and above it, the Paleocene ocean begins to fill in its own way, slowly and differently. The sharpness of the boundary in marine sites like this one was one of the key early arguments for a catastrophic, rather than gradual extinction event. If the extinction had been gradual, driven by climate change or sea level change or volcanic activity operating over millions of years, the boundary in the rock would be gradual too, a zone of transition rather than a line. The fact that the boundary is a line, that the Cretaceous community is present and then absent within the resolution of the geological record on this, points toward a sudden event. The sea above New Jersey was warm and shallow and full of life on the last day of the Cretaceous. The mosasaurs hunted in its depths. The schools of Encodus, the saber-toothed fish of the Cretaceous seas, its long curved teeth visible in hundreds of specimens from sites around the world, moved through the mid-water. The sharks circled below. The surface was rich with plankton, the base of the food web that sustained all of it. On the morning of the impact, the sea above New Jersey would have experienced the effects within hours, not the impact itself. The Chicxulub crater in Mexico was thousands of kilometers away. But the global effects, the shock wave moving through the water, the ejecta falling from the sky, the seismic waves propagating through the ocean floor. Within hours, the shallow sea above New Jersey was in distress. Within days, the falling debris and the atmospheric disruption had begun to affect the surface ocean chemistry. Within weeks and months, the collapse of marine productivity, the phytoplankton that formed the base of the food web, was underway. For the mosasaurs, the collapse of the food web was the immediate threat. An apex predator at the end of a long food chain is more vulnerable to the collapse of that chain than an animal at the bottom of it. When the plankton productivity drops, the fish that eat the plankton drop. When the fish drop, the mosasaurs that eat the fish starve. The cascade moves upward through the food web with a speed and completeness that no individual large predator can escape. The last mosasaurs in the shallow sea above New Jersey, if this was indeed the last place they were, would have been starving. Not dramatically, not all at once, but the slow, inexorable starvation of an ecosystem in collapse. The hunting grounds were emptier, the prey was smaller and scarcer. The energy balance that had sustained their enormous bodies for decades was shifting toward deficit. The individual mosasaur in the last months of the Cretaceous would not have known why its world was changing. It would have known the change, the scarcity of food, the changed quality of the water, the absence of sounds and movements that had previously been reliable features of its environment. But the asteroid, the global winter, the collapse of marine productivity, these were not within its capacity to perceive as a cause. It was simply in a world that had become, for reasons it could not access, less hospitable, and it responded in the only ways available to it, moving to find food, hunting more widely, eating prey it would previously have ignored, until even those strategies were insufficient. The last mosasaur in the shallow sea above New Jersey was not a dramatic death. It was a quiet one. The slow failure of an animal that had been a successful predator for 20 million years in a world that had stopped supporting what it was. The bones settled to the seafloor in the fine sediment that was already carrying the chemical signature of the asteroid winter. They were buried, they were mineralized, and then, 66 million years later, they were dug out of a New Jersey marl pit by a paleontologist who recognized them for what they were. The slow dissolve of the Cretaceous sea is preserved in that New Jersey pit, layer by layer, the fossils becoming sparser and then absent above the iridium line. The story is in the rock, patient and specific, waiting for the question that will draw it out. And above the boundary, the recovery, the new ocean slowly filling. New plankton, different from the Cretaceous plankton. New fish, different from the Cretaceous fish. The long rebuilding of the marine ecosystem from the survivors, the sharks which made it through, the rays which made it through, the bony fish, many lineages of which made it through, into the richness of the Eocene ocean and beyond. The sea above New Jersey today is the Cretaceous sea's successor, 66 million years on. It has its own mosasaur equivalent, the great white shark, the blue whale, the sperm whale hunting squid in the deep water. Different in form, continuous in function. The role of large marine predator did not disappear with the mosasaurs. It was empty for a while, and then it was filled again, by different animals following different evolutionary pathways to the same ecological position. The ocean does not stay empty. Nothing stays empty in geological time. The space created by extinction is the space filled by evolution. The two processes are not opposed, they are partners in the oldest dance there is. Let the slow certainty of that partnership be the last thought of this section. The darkness is always followed by filling. The empty is always followed by the new. The night is always followed by the morning that does not yet know what it will contain. The recovery from the KPG extinction happened at different rates in different parts of the world, and the variation tells us something important about the nature of extinction and recovery as ecological processes. In regions close to the impact site, in parts of North and Central America, in the marine environments of the Gulf of Mexico and the surrounding seas, the effects were most severe and the recovery slowest. The immediate physical effects were most intense here: the shock wave, the heat pulse, the tsunami generated by the impact, the ejecta falling back to Earth in these regions while other regions were still hours away from receiving it. The ecosystems closest to Chicxulub had the least to recover from in one sense. They were simply gone, emptied, the slate wiped cleaner than anywhere else. The recovery required building from the very simplest biological components. In regions farthest from the impact, in what is now New Zealand, in parts of Antarctica, in the southern hemisphere generally, the effects, while globally devastating, were less immediately catastrophic in the physical sense. Organisms in these regions had slightly more time between the impact and the most severe effects, slightly more survived, the recovery had slightly more to work with. This gradient of impact and recovery produced a world in the early Paleocene that was patchy. Different regions at different stages of recovery, different lineages surviving in different places, the early Paleocene fauna and flora varying significantly from region to region in a way that the late Cretaceous did not. The patchiness was itself an evolutionary opportunity. Different lineages surviving in different regions produced multiple independent centres of evolutionary diversification. The early Paleocene was a world of experiments running in parallel, different animals, in different regions, filling the available ecological space in different ways. Some of these experiments succeeded and spread, others remained regional and eventually went extinct. The interplay between the regional experiments and the global recovery produced the Eocene world's diversity. This principle, that diversity arises from the interaction of multiple independent experiments rather than from a single lineage's steady progress, is one of the deep patterns of evolutionary history. The Cambrian explosion was an extreme version of it, dozens of different body plans appearing in a relatively short geological interval, most of them eventually going extinct, the surviving ones producing all the animal diversity of the subsequent 500 million years. The post-KPG recovery was a less extreme version of the same principle. The experiments that fail are not failures in any meaningful sense. They are explorations of the possibility space, genuine attempts at viable biology that did not prove sustainable in the long run but contributed to the overall picture of what is possible and what is not. The creodonts were a genuine exploration of the large predator niche. The multi-toed early horses were a genuine exploration of ungulate body plans. The large flightless birds of the Eocene, the terror birds of South America, the gastornids of Europe and North America, were genuine explorations of the apex predator niche in the absence of large mammalian carnivores. Most of the Eocene experiments are not with us today. The creodonts are gone, the gastornids are gone, the multi-toed horses are gone. The specific forms that filled the post-extinction world in the first tens of millions of years of the Paleogene were, in most cases, transitional, real and successful in their own time, but the precursors of more successful forms rather than permanent fixtures of the biosphere. Even the forms that are still with us today are temporary, in geological time. The horse, the elephant, the rhinoceros, the whale, all are the current versions of lineages that will eventually produce future forms, or go extinct, or both. Nothing in the biological world is final. Every form is in process, every lineage is in motion, every current state is a way station between what came before and what will come after. This is not unsettling if you hold it at the right scale. At the scale of a human lifetime, the stability of the biological world is real and reliable. The species are what they are. The ecosystems are what they are. The world is recognizably continuous from year to year. At the scale of millions of years, nothing is stable, but that scale is so far beyond human experience that it can be held as a kind of philosophical background rather than a source of anxiety. You are a way station too, not just biologically. Your lineage will produce future forms if the lineage continues that are different from what you are. But also personally, the person you are now is a way station between the person you were and the person you will become. Everything is in process. Everything is transitional. This is not a flaw in the design. It is the design. The Paleocene dawn, with its recovering world and its patchy experiments and its quiet sense of a world not yet settled into its next stable form, holds a kind of companionship for anyone who feels themselves to be in transition. The world has always been in transition. The feeling of being between what was and what will be is the universal condition of life in geological time. You're between last night and tomorrow. You're in the transition that every night is, the necessary passage between one day and the next, the dark space where the self is briefly released from its daytime obligations and restored for its next version. The Paleocene was the necessary passage between the Cretaceous and the Eocene. It was not the best of times, but it was real, and it was doing essential work, and from it came everything that followed. You are doing essential work right now. The work of the dark, the work of the transition, the work of being in the between. Rest in that work, let it complete. The Eocene is on its way. Chapter 4. The Architecture of the Giant. In the Patagonian desert of southern Argentina, where the earth is pale and dry and the wind moves without interruption across an enormous emptiness, there is a quarry where the largest animal that ever walked on land was found. Its name is Patagotitan mairum. It lived approximately 100 million years ago in the mid-Cretaceous, in a landscape that was at that time not a desert but a warm floodplain, green, wet, crossed by slow rivers, rich with the plant life that a titanosaur required to sustain itself. The titanosaurs were the largest of the sauropod dinosaurs, themselves the largest group of dinosaurs overall, themselves the largest land animals that have ever existed. Within that group of giants, Patagotitan was among the largest of all. Its weight has been estimated at between 65 and 70 tons. For reference, an African elephant, the largest living land animal, weighs between 5 and 7 tons. A Patagotitan was roughly 10 to 12 elephants, stacked vertically or arranged end to end, somehow integrated into a single coherent animal that breathed, moved, fed, reproduced, and eventually died in the warm mid-Cretaceous. How was this possible? The answer is in the bones, and the bones are extraordinary. A titanosaur vertebra from the neck region, and the neck of Patagotitan was perhaps 12 meters long, is not what you would expect a weight-bearing vertebra to look like. It is not dense, it is not solid. It is instead a structure of hollow chambers and thin bony partitions, like the internal structure of a bird's feather or the cross-section of a modern high-rise building's load-bearing column. The technical term is pneumatization, the same term used for bird bones, and the air sacs that filled these chambers were connected to the respiratory system, meaning that the titanosaur's skeleton was not merely scaffolding, but part of the breathing apparatus itself. A Patagotitan was, in a structural sense, partially made of air. Its enormous neck contained more space than substance. The thin, bony struts that divided those air-filled chambers were arranged in geometric patterns that bear a striking resemblance to the internal architecture of Gothic cathedrals: flying buttresses, pointed arches, load-distributed lattices designed to carry enormous weight with minimal material. This is not a metaphor pulled from human architecture and applied to nature. It is the reverse. The engineers of the great medieval cathedrals were, without knowing it, reinventing solutions that evolution had discovered in the ancestors of birds 100 million years before. Walk slowly around the cast of a Patagotitan in your imagination. Begin at the tail, long tapering held out behind the body as a counterweight to the neck. Run your eyes along the flanks. The torso is barrel-shaped, deep-chested, its ribs describing a space large enough to contain a small house. The legs are columnar, straight, built for compression rather than rotation, more like the pillars of a building than the limbs of an animal in any conventional sense. Each foot, each enormous 5-toed foot, would have left a print approximately a metre across in soft ground. Now move your gaze upward, along the shoulder and into the neck. Here is where the mathematics of the impossible becomes beautiful. The neck of a large sauropod is one of the strangest structures in the history of animal life, long enough and massive enough that simple engineering calculations suggest it should not be able to support its own weight, let alone the weight of the head at the end of it. The solution evolution found was the pneumatized vertebrae already described, combined with a system of ligaments and muscles running along the top of the neck that worked like the cables of a suspension bridge, redistributing the load, allowing the neck to remain elevated with less muscular effort than a solid boned neck of the same length would have required. The head, at the end of this extraordinary structure, is surprisingly small. In proportion to the body, a titanosaur's head is almost laughably modest, a small, blunt thing with pencil-like teeth, designed not for chewing but for stripping foliage, like a rake drawn through vegetation. Titanosaurs did not chew their food. They swallowed it whole, and the processing was done by gastroliths, stones swallowed deliberately and held in the stomach, where the mechanical action of the stomach walls and the stones together ground the plant material into digestible pulp. In some titanosaur specimens, collections of smooth, worn stones have been found in the abdominal region, the last evidence of a digestive strategy that required an animal to eat rocks. Now consider the scale of the appetite this body required. The largest modern elephants eat approximately 300 kilograms of vegetation per day. A Patagotitan, with a body mass 10 times greater, would have required something in the order of several tons of plant material daily. It spent most of its waking life eating. The long neck was not primarily a feature for reaching high branches, though it could do that. It was primarily a feeding strategy that allowed the animal to sweep a large arc of vegetation from a single standing position, maximizing the energy gained per unit of movement. Each step this animal took required significant energy expenditure. Standing still and sweeping the neck was metabolically efficient in a way that constant movement was not. Which means that a Patagotitan, for much of each day, was essentially stationary. A 10-metre pillar of neck moving slowly across an arc of Cretaceous floodplain, the head dipping and rising, stripping vegetation with quiet mechanical efficiency. The sound of this would have been unremarkable. The soft tearing of plant material, the low digestive rumblings of a system processing tons of food, the deep regular percussion of a heartbeat that research suggests may have beaten as slowly as 4 or 5 times per minute in a fully adult animal at rest. Imagine standing at the edge of that Cretaceous floodplain and watching. Not close. Nothing about this creature would invite closeness, not from aggression, which was probably rare in a well-fed herbivore, but simply from scale. From a distance of perhaps 200 meters, you could see the full length of the animal. You could watch the neck arc from right to left, slowly, the head dipping to the vegetation. You could see the flank rise and fall with each breath. You could feel, through the ground beneath your feet, the occasional distant compression of each footstep. The earth remembers those footsteps. Sauropod trackways have been found at dozens of sites around the world, in Spain, in Wyoming, in Morocco, in Portugal. The tracks are sometimes found in parallel, multiple animals moving in the same direction, suggesting herds, or at least loose social groupings. In one site in Spain, the trackway evidence suggests a group of at least 15 animals moving together, a mixed-age herd, the prints of smaller juveniles preserved alongside the enormous impressions of the adults. A herd of 15 titanosaurs moving across a Cretaceous floodplain, the ground trembling at a frequency below easy hearing, the horizon alive with slow-moving necks, rising and falling like the masts of ships in a gentle swell, the sound of 15 vast bodies breathing, the rhythm of it deep and unhurried as regular as tidal movement. Then silence as the herd passes. The trees at the edge of the floodplain, bent slightly by the passage of bodies larger than they are, slowly straighten. The water that had been disturbed in the river shallows settles back into its usual patterns. The insects return to their continuous singing. The Cretaceous afternoon resumes. You are breathing with the memory of those breaths, slow, deep, unhurried. The body at rest is doing something ancient and enormous in its simplicity. Every breath you take tonight is part of a lineage of breaths, stretching back through every animal that has ever lived, back through the titanosaurs and their vast slow exhalations, back through every creature that developed lungs, back through the first cellular machinery that learned to extract energy from air. You are not separate from the giant. You are, in the deepest sense, a continuation of it. Everything that lives on land today carries in its cells the legacy of animals that were, in their time, equally committed to the simple act of existing. The Patagonian desert is cold tonight, dry and starlit. But in the warm Cretaceous floodplain that the desert once was, something enormous breathes slowly in the dark, and the earth beneath it holds that weight with patience, as the earth has always held the weight of the living. Let the night hold your weight now with the same patient steadiness. The sauropod egg is the beginning of the impossible. It is a small thing, roughly the size of a volleyball, containing everything required to produce an animal that will grow to weigh 70 tons. The improbability of this is not a figure of speech. It is a genuine, measurable fact that has occupied the attention of paleontologists and biomechanists for decades. Consider the mathematics. A Patagotitan at full adult size weighed approximately 65 to 70 tons. The egg it hatched from weighed perhaps 2 kilograms. The ratio is roughly 35,000 to 1. For comparison, a blue whale, the largest animal alive today, has a ratio of birth weight to adult weight of approximately 1 to 15, roughly 30 times less dramatic than the titanosaur's egg-to-adult ratio. The juvenile titanosaur that hatched from that 2-kilogram egg was the size of a large cat. It was, presumably, precocial, capable of walking and feeding independently within hours or days of hatching, as most large reptiles are, and as the evidence of titanosaur nesting sites, which do not show the evidence of prolonged nest occupation found in hadrosaur sites, suggests. The hatchling walked away from the nest into a Cretaceous world that was, from the perspective of a 2-kilogram animal, full of predators and very large plants. Its growth rate was extraordinary. Study of bone growth rings in sauropod fossils, the same technique used to age trees, applied to dinosaur bone, reveals that large sauropods grew at rates far exceeding those of any living reptile, and comparable to or exceeding those of the largest living mammals. During peak growth phases, a juvenile titanosaur may have been adding several kilograms of body mass per day. The metabolic requirements of this growth rate were themselves extraordinary. The animal was essentially a food processing machine, converting plant material into body mass at a rate that has no modern analogue. The teeth of sauropods were simple pegs or spoons or rakes, tools for stripping vegetation, not for processing it. The processing happened in the gut, aided by the gastroliths already mentioned, and by a digestive system that must have been proportionally enormous, given the scale of the input and the relatively poor nutritional density of the Cretaceous plant material available. Some estimates suggest that a large titanosaur may have spent as many as 18 to 20 hours per day feeding, its long neck sweeping back and forth through a Cretaceous forest like a living harvesting machine. The pneumatized vertebrae that made this neck possible were not just a weight-saving measure, they were an active part of the respiratory system. The air sacs connected to them were part of a bird-like unidirectional airflow respiratory system, far more efficient than the tidal breathing of mammals, which requires that air be pushed in and out of the same space, and therefore never achieves full exchange of gases. The sauropod respiratory system moved air through the lungs continuously, ensuring maximum oxygen extraction with every breath, necessary for an animal that needed to sustain the metabolic demands of its impossible size. The sauropod body was, in every system, optimized for scale, not optimized in the way that an engineer optimizes a design, not with foresight or intention, but optimized in the evolutionary sense, by the slow accumulation of variations that worked better than the variations they replaced, over millions of generations, until the animal that resulted was as large as land-based life can be while still functioning. There is a theoretical maximum size for a land animal, set by the physics of bone strength and muscle attachment and metabolic demand. Patagotitan was close to that maximum. Whether any land animal could have been significantly larger is debated. The constraints are multiple and interacting, and the question of what would have happened to sauropod body plans if the Cretaceous had continued for another 20 million years is one of those tantalizing impossibilities that paleontologists discuss late at night in the way that physicists discuss parallel universes. What is certain is that the Cretaceous produced something that has not been produced since. A land animal so large that its body was partially made of air, sustained by a respiratory system so efficient that it could extract oxygen from the atmosphere faster than any mammal of comparable size, growing from an egg the size of a volleyball to a weight of 70 tons in 3 or 4 decades, moving through the landscape with the confidence of something that has, in the most literal sense, no natural enemies in its adult form. The tracks of sauropods in the Spanish, Moroccan and North American trackway sites tell of the sheer physical reality of their passage. The prints are deep, even in hard sediment. The stride length is enormous. In some sites, the parallel trackways of multiple animals moving together suggest the unhurried, confident movement of animals that know they are the largest things in the landscape. Imagine being inside the herd, standing in the late Cretaceous afternoon on the edge of a floodplain as the herd moves past, the ground trembling continuously, not in discrete footfalls, but as a single extended vibration that rises through the soles of your feet and into your legs and your chest. The smell, warm, heavy, the smell of large animals and the vegetation they have disturbed, the particular organic richness of a Cretaceous floodplain disrupted by the passage of thousands of tons of moving body mass. And above you, the necks, 12 meters of neck above each animal, moving with the slow pendulum swing of the feeding sweep, the small heads on their improbable scaffolding cutting through the afternoon air. The sound of vegetation being torn, amplified by the number of animals involved, a continuous soft tearing that is almost musical in its regularity. Then the herd has passed. The ground trembling fades. The vegetation behind them is stripped to a height of 12 meters. The lower levels of the forest canopy browsed away, the ground compacted by enormous feet. The landscape has been changed by the passage of the herd in ways that will persist for months. The compacted soil, the stripped vegetation, the altered water drainage of footprint depressions that become seasonal pools. The sauropods were not simply animals living in a landscape, they were a geological force. Their bodies were so large and their numbers in the right habitats so great that they shaped the Cretaceous landscape as much as the landscape shaped them. They were, in the technical language of ecology, ecosystem engineers, organisms whose activities alter the physical environment in ways that create or modify habitat for other species. The Cretaceous floodplain, after the herd has passed, settles into a new quietness. The evening's coming on, the temperature is dropping slightly, the warm Cretaceous afternoon giving way to the warm Cretaceous evening. Small animals are emerging from the undergrowth, moving through the disrupted vegetation, taking advantage of the changed landscape in ways specific to their own needs. The sauropods move on. Their footsteps are already growing distant, the vibration fading, the sound of their passage becoming part of the general evening sound rather than its dominant feature. And the night comes down, slow and warm, over the floodplain and the stripped forest margins and the compacted footprint pools that are already filling with the first shallow water of the evening dew. Rest in that warmth. Let the evening of the Cretaceous hold you with the same patience that it held everything else that ever rested inside it. The question of sauropod thermoregulation, how an animal so large managed its body temperature, has been one of the most productive research questions in recent paleontology, because the answers have implications not just for sauropods, but for our understanding of dinosaur physiology generally. For most of the 20th century, dinosaurs were assumed to be ectothermic, cold-blooded in the popular sense, meaning that their body temperature was largely determined by external conditions rather than by internal heat production. This assumption was based on their classification as reptiles, and reptiles are ectothermic. The problem with the assumption is that it does not fit the evidence particularly well. An ectothermic animal the size of a large sauropod would have an enormous thermal mass. Thermal mass is the capacity of an object to absorb and retain heat. A large object retains heat longer than a small one, because the ratio of surface area to volume decreases as size increases. A 60-ton sauropod, even if it produced no internal heat at all, would be extraordinarily slow to heat up and cool down. The daily temperature swings that create problems for small ectotherms, the lizard that must bask for an hour before it can move effectively in the morning, would be essentially irrelevant to an animal of sauropod scale. The term gigantothermy was coined to describe this property, the maintenance of a relatively stable body temperature through sheer body mass, independent of whether the animal produces internal metabolic heat. A gigantotherm is neither warm-blooded nor cold-blooded in the conventional sense. It is simply so large that the external temperature variation is too slow to significantly affect its core temperature. But the evidence from bone histology suggests that the story is more complex than gigantothermy alone. The growth rings preserved in sauropod bone, the same rings used to estimate age, show growth rates consistent with high metabolic activity. Slow ectothermic growth rates would produce different growth ring patterns than those found in sauropod bone. The patterns found suggest a metabolism that was elevated above the ectothermic baseline, possibly significantly elevated. The current consensus, to the extent that one exists, is that large dinosaurs, including sauropods, were probably mesothermic, intermediate between the low, externally dependent metabolism of modern reptiles and the high, internally regulated metabolism of modern mammals and birds. Not fully warm-blooded in the mammalian sense, but not cold-blooded in the reptilian sense either. Something in between, perhaps with a capacity to adjust metabolic rate depending on conditions, elevated during periods of high activity, reduced during rest. This model of dinosaur physiology has interesting implications for behavior. A mesothermic animal can be active in conditions that would slow down a true ectotherm. It does not need to spend the morning basking before it can move. It can function at night, in cool temperatures, in ways that a crocodilian cannot. But it also does not have the continuous high metabolic cost of full endothermy. It can afford to rest for long periods without its body temperature dropping, to the point where activity becomes impossible. The T-Rex resting in the Montana afternoon, the image introduced early in this script and returned to throughout, fits this model. An animal that rested for long periods, conserving energy, but was capable of rapid and sustained activity when the situation demanded it. Not the sluggish crocodilian that must bask to function, not the continuously active mammal that must eat constantly to fuel its metabolic furnace. Something in between, with the specific advantages and limitations that a mesothermic physiology would provide. The sauropods, with their enormous thermal mass supplementing whatever endogenous heat production they managed, were probably the most thermally stable of all the dinosaurs. Their core temperature, once established in the warmth of the Cretaceous, would have varied little over the course of a day or even a season. They were, in this sense, living rocks, enormous masses of biological material whose temperature was more like the temperature of the environment than the temperature of an animal with a regulated internal thermostat. Walking among them would have been, in thermal terms, like walking near warm stone. Not the sharp, directed warmth of a mammal's body heat, but the diffuse, ambient warmth of a very large object that has been in the sun all day and is radiating its absorbed heat back into the cooling evening air. The air around a resting sauropod herd at dusk would have been warmer than the surrounding landscape, a zone of elevated temperature created by the combined thermal mass of dozens of enormous bodies. Small animals, the mammals, the lizards, the insects, would have known this. Some of them may have sought the warmth of the sauropod herd's thermal zone at night, gathering in the slightly warmer air around those enormous passive radiators, benefiting from the temperature differential created by the presence of the giants. This is a kind of unintentional mutualism, the large animal providing warmth it did not intend to provide, the small animal benefiting from it without any interaction with the large animal at all. The ecosystem is full of these unintentional relationships, these accidental benefits that flow from the activities of one organism to another, without any awareness or intention on either side. You are currently benefiting from the unintentional activities of millions of organisms, the plants that produce the oxygen you breathe, the microorganisms that cycle the nutrients in the soil, the bacteria in your gut that process the food you eat. None of them intend to benefit you. None of them are aware of you. They are simply doing what they do, and what they do happens to be necessary for your existence. The night is full of these unintentional kindnesses. The world is doing what the world does, and what it does is, on balance, compatible with your continued existence. That is not a small thing. That is the accumulated result of 4 billion years of interdependence, each organism doing its thing, the aggregate of all those things producing conditions in which you can lie in the dark and breathe slowly and rest. The sauropod herd, warming the air around it in the Cretaceous dusk, the small mammals gathering in the warm zone at the edge of the herd, the Cretaceous night settling over all of it, warm and patient, holding everything that lived in it with the same impartial gentleness. Let that impartial gentleness hold you now. The night does not differentiate. It holds the large and the small with the same dark warmth. You are held in it right now, as everything has always been held. The question of sauropod locomotion, how an animal weighing 60 or 70 tons moved through the world, has been approached through several lines of evidence, each yielding a different dimension of the answer. Trackways are the most direct evidence of locomotion, actual footprints, in the order in which they were made, preserving the step length, the stride length, the width of the trackway, and sometimes the depth of each impression. From these measurements, biomechanists can calculate the approximate speed of the animal, the pattern of weight distribution across the foot, and whether the animal was walking steadily or varying its pace. The trackways of sauropods consistently show a walking gait, no running, no galloping, no bounding. The mathematics of large animal locomotion make running essentially impossible at titanosaur scale. The forces generated during the aerial phase of a running stride, when all 4 feet are off the ground simultaneously, would be enormous, and the skeletal structures capable of withstanding those forces would be far heavier than anything compatible with a functional animal. Large sauropods walked. They walked their entire adult lives, and walking was sufficient. A creature that eats 3 tons of vegetation per day does not need to chase it. The walking speed of a large sauropod, calculated from trackway data, was approximately 4 to 7 kilometers per hour, roughly the walking speed of a tall human. The stride length was enormous, each step covering several meters, but the frequency of steps was slow, producing an overall pace that was deliberate and unhurried. An adult sauropod walking at this speed had a quality of movement that observers on the trackway record would have perceived as majestic rather than urgent. The footfall sequence of a sauropod was probably similar to that of a modern elephant, a 4-beat walk in which each foot hits the ground separately, in a regular sequence, producing a regular rhythmic percussion. The sound of this, 4 massive footfalls in sequence, each one a deep compression of soft ground, each one separated from the next by a fraction of a second at walking speed, would have carried considerable distance through the ground as well as the air. The ground vibration from a moving sauropod herd was probably detectable by other animals at considerable distance. Modern elephants communicate through seismic signals, low-frequency vibrations produced by foot stamping that travel through the ground and are detected by other elephants via vibration-sensitive receptors in their feet and through their leg bones. If sauropods used a similar form of seismic communication, and the structural similarities between their locomotion and elephant locomotion make this plausible, the ground itself was a communication medium, carrying information about the location and movement of large animals to other animals with the receptors to detect it. Small animals on the Cretaceous floodplain would have known, through the soles of their feet or the touch receptors in their belly if they were prone, when a sauropod herd was approaching and from which direction. The ground would have told them. The seismic signature of a moving titanosaur, the specific rhythm of its footfalls, the specific frequency of the ground vibrations it produced, was information available to every animal in contact with the ground for hundreds of meters in every direction. the world is still full of seismic communication. The vibrations of machinery, of traffic, of the very low-frequency sounds produced by large engines and by ocean waves propagate through the ground continuously. Some animals, elephants, many insects, possibly some fish, can detect these vibrations and extract information from them. You may be less aware of this channel than the animals around you, because human seismic sensitivity is not highly developed, but the channel is there. The floor beneath you right now is transmitting information. The vibrations of the building, the slow settling of the structure, the movements of other occupants if there are any, the low-frequency hum of ventilation systems, are propagating through the floor and into your body. You're not consciously processing this information, but your body's in contact with it. The seismic world is present around you, as it has been present around every animal in contact with the ground since the first animals developed contact with solid substrate. The titanosaur's footsteps travelled through the Cretaceous ground for hundreds of meters. The ground received them and transmitted them. The small animals on the floodplain felt them and responded, adjusting their movements to account for the approach of the enormous. And then the herd passed, and the ground returned to its background level of vibration. The insects underground, the roots moving in the slight breeze, the river running over its bed of gravel, and the small animals returned to their foraging, and the Cretaceous afternoon continued. The world settles after the large things pass. The ground returns to its quiet. The background is always there, beneath the foreground, patient and continuous. Your world is settling now too. The large things of the day are passing. The ground of the night is receiving you. The seismic signature of your day is being absorbed into the quiet substrate of the night. Feel the floor beneath you, the mattress, the firm or soft surface, receiving your weight as it always has, as every ground has always received the weight of whatever rested on it. Patient, sufficient, reliable. The sauropods have long since passed. The ground remembers their footsteps in the fossil trackways. But tonight the ground is quiet and you are resting on it, and the silence of the Cretaceous floodplain after the herd has moved on is the silence you are moving into now. The eyes are the first thing you notice. Not the teeth, not the claws, not the overall body plan that places this creature in the company of the familiar theropods. The eyes. They are enormous relative to the skull, forward-facing in the way that predator eyes tend to be, arranged to maximize depth perception, to allow precise judgment of distance, to create the overlapping fields of vision that enable a hunter to track moving prey without losing its precise three-dimensional location. But it is not just their size or position that catches your attention, it is their quality. The iris is large and the pupil is wide, adapted for low light. This animal sees best not in the full brightness of the Cretaceous day, but in the long, attenuated light of dusk and early dark. This is Troodon. You have already visited it briefly in the night chapter. Now you stay longer. Troodon formosus, the name means beautiful wounding tooth, a paleontologist's compression of observation and poetry, lived in the late Cretaceous of North America, in the forests and floodplains of what is now Montana and Alberta. It was approximately 2 meters long, roughly the height of a tall human when standing fully upright. It weighed perhaps 50 kilograms, the weight of a large dog or a medium-sized deer. It was fast, its legs long and lightly built, its foot bearing the distinctive enlarged inner claw of the dromaeosaurid and troodontid theropods, the sickle claw, that curved blade of bone that it could have used as a pin or a hook to hold struggling prey. But the sickle claw is not what makes Troodon remarkable. What makes Troodon remarkable is the space inside its skull where the brain was. Brain endocasts, the shapes preserved inside fossil skulls, are among the most haunting objects in paleontology. They are not brains. The brain itself is soft tissue and does not fossilize. What preserves is the shape of the space the brain occupied, sometimes in extraordinary detail. From this shape, scientists can infer which parts of the brain were large or small, how they were arranged, something of the cognitive priorities of the animal that owned the brain. Troodon's brain endocast shows a brain that was, relative to body size, larger than any other known non-avian dinosaur. The encephalization quotient, the ratio of actual brain size to the expected brain size for an animal of a given body mass, was comparable to that of modern emus or ostriches, which is to say, comparable to that of large living birds, and large living birds as a group are not stupid. Ostriches solve novel problems. Emus demonstrate long-term memory and social learning. The corvids, crows, ravens, jays, are among the most cognitively sophisticated non-human animals we know, capable of tool use, future planning, complex social reasoning, and what some researchers cautiously describe as a theory of mind. Troodon was not a crow. Its brain, for all its relative size, was organised differently from a crow's brain, and the cognitive capabilities it supported were shaped by entirely different evolutionary pressures. But it was, by every measure available to us, doing something with that brain. The enlarged optic lobes suggest complex visual processing. The relatively developed cerebellum suggests sophisticated motor coordination. There was more going on inside that skull than simple stimulus-response behaviour. What was it like to be Troodon at night? The question sounds strange. We do not usually ask what it was like to be something. But the question has a serious meaning, and the evidence in the fossil record points towards something like an answer. Troodon was almost certainly active at night or at twilight. Its forward-facing, large-eyed, low-light adapted visual system was built for the specific conditions of a Cretaceous dusk, when the small mammals and reptiles it likely preyed upon were also active, moving through the leaf litter in search of their own prey, and when the larger daylight predators would have retired to rest. Troodon moved through the dusk forest with what we can infer was precise, alert attention, not the continuous automatic attention of a less cognitively developed animal, but something more like the focused, selective attention of a creature that could distinguish relevant from irrelevant sensory information, that could plan, in a basic sense, the next few seconds of a hunt. The nesting behaviour of troodontids adds another layer. Fossils of troodontid eggs have been found in carefully constructed nests, the eggs positioned upright in pairs, an arrangement that differs from the flat-on-their-sides egg positioning of many other dinosaurs and suggests a more active management of the clutch, a more direct involvement of the parent with the physical arrangement of the eggs. In some specimens, an adult skeleton has been found in or near the nest, in a posture consistent with brooding, sitting on or near the eggs to provide warmth, to guard against predators, to maintain the specific conditions the developing eggs required. A Troodon, crouching over its nest in the Cretaceous dark, aware of its eggs beneath it, aware of sounds in the forest around it, maintaining its attention across the long hours of a prehistoric night. Not thinking about this in any human sense, not reflecting, not planning weeks ahead, not worried about tomorrow, but present, engaged with the specific reality of eggs beneath and forest around. This is intelligence, not human intelligence, not the intelligence that produces language and mathematics and art, but the older intelligence, the intelligence that reads the world through sensory experience, that learns from experience, that responds to the specific rather than the generic, that has in some sense a stake in what happens next. Now consider Maiasaura. The name was chosen deliberately. Maiasaura means good mother lizard, and it was chosen because of what the fossils showed. Maiasaura was a large hadrosaur, a duck-billed dinosaur that lived in Montana about 75 million years ago, in the same general time and place as Triceratops and T-Rex. It was not a predator. It was a large herd-living herbivore, probably 7 or 8 meters long as an adult, with a broad, flat, toothless beak characteristic of the hadrosaurs, and the elaborate dental battery in the back of the mouth that allowed it to process tougher plant material than most herbivores of its size. The nesting sites discovered in Montana in the 1970s changed our understanding of dinosaur behaviour entirely. The nests were colonial, dozens of nests in a single area, regularly spaced, suggesting that the animals returned to the same nesting site year after year, a behaviour seen today in colonial nesting seabirds like albatrosses and penguins. Each nest was a mound of earth and vegetation, perhaps 2 meters across, with a shallow depression in the top for the eggs. The eggs were arranged in concentric rings, suggesting careful placement. But it was the juvenile bones inside and around the nest that told the most important story. The juveniles found at the nesting sites were not newly hatched. They were older, weeks or months old, and their leg bones showed that they had not yet fully ossified, that they were not yet capable of sustained independent movement. Their teeth showed where they had been eating. Their presence in and around the nests, combined with the presence of plant material in the nests that had been brought there from outside the nesting area, pointed unmistakably to a single conclusion. Maiasaura parents brought food to their young. They did not hatch their eggs and move on, as many reptiles do, leaving the hatchlings to fend for themselves. They stayed. They gathered plant material and carried it, or herded the young toward it. They maintained the nest as a home base for weeks or months after hatching, until the young were mobile enough to join the larger herd. This is parental care in a fully meaningful sense, not instinctive egg guarding, but ongoing, active, post-hatching investment in the survival of specific offspring. A Maiasaura parent watching over a nest of young in the late Cretaceous dusk. The young are unsteady on their feet. They cluster around their parent with the pressing, insistent closeness of young animals that have not yet learned to be separate from the warmth and safety of the large body nearby. The parent is alert to sounds in the surrounding vegetation. Its long neck swings slowly, scanning. Its large eyes move through the qualities of light that are changing as the day ends. This is care, not metaphorical care, not care projected backward by human sentimentality. Structural, behavioural, fossilized care. Care preserved in the positions of bones and the wear patterns of teeth and the arrangement of egg fragments in ancient mud. The care you have received and given in your own life is part of the same lineage. Not directly. You're not descended from Maiasaura, but the impulse to protect the young, to bring food, to remain present through the long dark hours when something small and vulnerable is sleeping nearby. That impulse did not begin with mammals. It is older than that. It was present in the Cretaceous, fossilized in Montana mud, 160 million years before the first human parent watched over a sleeping child. The forest is quiet now around the nesting colony. The adults are settling, their large bodies arranged loosely around the nests. The young sleep in the nest's warmth, which is partly the warmth of accumulated plant material decomposing, and partly the warmth of bodies nearby. The stars of the late Cretaceous night are different from the stars of tonight. Some of the same, many different. The slow drift of stellar motion having moved them across the millennia. But the warmth is the same warmth. The quiet is the same quiet. The small body sleeping in it is just a different kind of small. Let yourself be that small for a moment. Let yourself be held in the warmth of something older and larger than your own history. The ancient night is very still. The hadrosaur dental battery is one of the strangest structures in the history of vertebrate evolution, and it tells a story about the level of investment that these animals made in the simple act of eating. Most toothed vertebrates have a single set of teeth at any given time. Mammals replace their teeth once, from juvenile to adult, and then work with those adult teeth for the rest of their lives. Crocodilians replace individual teeth as they wear, maintaining a continuous supply but never having more than a single functional tooth in each socket at once. Sharks have multiple rows, the replacement teeth moving forward as the front rows are lost. Hadrosaurs had none of these systems. They had a dental battery, a complex stacked arrangement of teeth in which hundreds of individual teeth were packed into a block of tooth material, arranged in columns and rows, with new teeth continuously developing below the surface to replace those worn away from the top. The functional surface of the battery was a single, flat, heavily abraded grinding surface, created by the wear of hundreds of individual tooth crowns packed so tightly that they formed a continuous surface rather than individual peaks. Examination of hadrosaur dental batteries under high magnification reveals that the different tissues of the individual teeth, enamel, dentine, cementum, had different hardnesses, and that the arrangement of these tissues in the battery created a self-sharpening surface as they wore at different rates. The harder tissues wore more slowly, creating microscopic ridges in the grinding surface that maintained the battery's effectiveness for processing tough plant material. This is engineering of extraordinary sophistication. Not designed engineering, evolved engineering, the product of millions of years of selection for the ability to process plant material that required more grinding than simpler tooth arrangements could provide. The hadrosaur dental battery is a solution to a specific ecological problem: how to efficiently process large quantities of tough, silica-rich Cretaceous vegetation that no other vertebrate lineage has independently developed. The investment in dentition reflects the investment in plant processing more generally. Hadrosaurs were, in their own ecosystem, the equivalent of modern bison or wildebeest, large, highly successful herbivores that could exploit plant resources that many other animals could not efficiently use, whose numbers could therefore be very large, and whose presence in the landscape shaped the vegetation and the ecology in significant ways. The bone beds that preserve multiple hadrosaur individuals together, sometimes dozens, sometimes hundreds of individuals in a single deposit, speak to the social nature of these animals and to the scale of events that could kill multiple animals simultaneously. Mass drowning events during river crossings, catastrophic floods, possibly drought, animals converging on diminishing water sources and dying together. The bone beds are not the ordinary background mortality of a population. They are exceptional events, preserved because the exceptional circumstances of mass death created exactly the conditions, rapid burial, multiple individuals in the same place, that allow fossilization. One bone bed in Alberta contains the remains of at least 5,000 hadrosaurs in a single layer. The implications of this are significant, not just for what it tells us about hadrosaur social behavior, that they moved in very large groups, at least at certain times and in certain places, but for what it tells us about the scale of Cretaceous animal populations. 5,000 individuals of a single species in a single event is not the entire population. It is a fraction of it. The actual population of hadrosaurs in the late Cretaceous of North America must have been very large indeed, in the tens of thousands at minimum, possibly far more. A world with tens of thousands of large hadrosaurs moving through it is a different world from the sparse, isolated individual world that the scale of the animals might suggest. It was a world full of large animals, full of the sounds of their passage and their communication, full of the ecological effects of their browsing and their movement and their death. The Cretaceous was not quiet. It was not lonely. It was, by any reasonable measure, louder and more densely inhabited by large animals than any landscape on Earth today. The current world is quieter than the Cretaceous. The megafauna that once populated every continent have been reduced, by the ice ages, by human hunting, by habitat loss, to a fraction of their former diversity and abundance. The African savanna, often held up as an example of wild abundance, is a pale shadow of what every continent once had. The Americas, before the arrival of humans 12,000 years ago, had mastodons and mammoths and ground sloths the size of elephants, lions and cheetahs and giant bears, horses and camels and tapirs, all of it gone now, or nearly gone. The Cretaceous had more species, more individuals, more ecological complexity, more sound and movement and biological energy per square kilometre. The land was full in a way that the modern land is not. And at night, all of it rested. The hadrosaur herds settled into their rest in the river margins. The ceratopsians arranged themselves in their small defensive clusters. The predators, whose energy expenditure in the hunt required recovery periods of substantial duration, rested in whatever cover they preferred. The Cretaceous night was full of sleeping animals, the full complement of the most successful fauna in the history of the Earth, doing the same thing that you're doing right now. The care those animals showed, the Maiasaura parent by the nest, the Troodon brooding its eggs, the social bonds maintained within hadrosaur herds, is not diminished by its distance from us. It is, if anything, made more significant. Care existed before mammals. Attention to the young existed before anything we would call conscious. The impulse to remain present, to maintain proximity to what is vulnerable, to be available in the night. These things were present in the Cretaceous, and they were there first. You did not invent the night watch, you inherited it. The question of pack hunting in dromaeosaurid dinosaurs, the group that includes Velociraptor and its relatives, has undergone significant revision in recent years, and the revision is instructive about how scientific ideas about dinosaur behavior develop and change. The image of Velociraptor as a coordinated pack hunter, groups of animals working together to bring down prey larger than any individual could subdue alone, became iconic through popular culture and persisted as a scientific hypothesis because it seemed to fit the anatomy. The enlarged sickle claw, the forward-facing eyes, the relatively large brain, all of these seem consistent with a sophisticated social hunter. The evidence for pack hunting in dromaeosaurids is in fact quite thin. The bone beds that preserve multiple dromaeosaurids together, most famously the Deinonychus bone beds associated with Tenontosaurus remains in Montana, do show multiple individuals of the same predator species in association with prey. But the interpretation of these bone beds as evidence of cooperative hunting has been challenged on several grounds. First, The presence of multiple predators with a prey carcass does not necessarily indicate cooperative hunting. Modern Komodo dragons will gather at a large carcass and feed simultaneously, but they do not cooperate in the hunt. Modern crocodilians will gather in large numbers at river crossings and take prey opportunistically, but this is not coordinated hunting. The association of multiple dromaeosaurids with a prey animal could represent opportunistic gathering, multiple individuals attracted to a carcass, or to the sounds and smells of a struggling animal, arriving independently and feeding or dying alongside each other. Second, some of the Deinonychus specimens from the Tenontosaurus bone beds show bite marks consistent with Deinonychus teeth, which suggests that the dromaeosaurids were eating each other as well as the prey, a behaviour not consistent with the cooperative hunting model, but entirely consistent with opportunistic gathering and feeding. Third, the brain size of dromaeosaurids, while relatively large for non-avian dinosaurs, is comparable to modern birds like emus and ostriches, animals that are not known for complex cooperative behaviour. The cognitive demands of coordinated pack hunting in the manner of wolves or lions require neural machinery that there is no strong evidence the dromaeosaurids possessed. What the evidence better supports is an opportunistic solitary hunting strategy, with the capacity to deal with larger prey through ambush, persistence, or targeting of vulnerable individuals, the young, the old, the injured. Not the dramatic coordinated attack of wolves, but the more common large predator strategy of finding and exploiting the weaknesses already present in a prey population. This is, in some ways, a less exciting picture than the coordinated pack hunter. But it is more plausible, and plausibility is a virtue in science that excitement is not. The dromaeosaurids were remarkable animals, fast, agile, cognitively sophisticated by the standards of non-avian dinosaurs, equipped with a weapon in the sickle claw that had no direct equivalent in any other Cretaceous predator. They did not need the additional implausibility of coordinated wolf-like hunting to be impressive. What they were is already enough. The social lives of dromaeosaurids remain genuinely unknown. Whether they were entirely solitary, whether they formed temporary associations around food resources, whether there was any form of pair bonding or parental care beyond egg brooding. The evidence does not allow confident conclusions. The nesting evidence suggests brooding. The bone beds suggest at least occasional aggregation. Beyond that, the specific texture of their social lives is in the category of things that the fossil record cannot currently recover. What can be said is that Velociraptor and its relatives lived in a world of social complexity larger than their own species. The Cretaceous ecosystem in which they operated was full of animals whose behaviours they needed to read accurately to survive. The size and direction of herbivore herds, the locations and habits of other predators, the seasonal patterns of the landscape. The intelligence evidenced by their brain structure was deployed in reading that complex world and responding to it effectively. The sickle claw, on the inner toe of the foot, is often described as a slashing weapon, the idea being that the dromaeosaurid leaped onto its prey and slashed with the claw in the manner of a tiger's dew claw. Biomechanical analysis has complicated this picture. The claw's curvature and the muscle attachment evidence suggest that it was more likely used as a gripping hook, seizing prey and holding it in place rather than slashing through it. Experimental work with scaled models in comparison with living raptorial birds suggests that the dromaeosaurid hunting technique may have resembled the prey restraint technique of modern eagles and hawks, seizing with the feet and holding while the prey struggles to exhaustion, the beak doing the killing work rather than the claws. An eagle scaled to the size of a large turkey, hunting in the warm late Cretaceous afternoon with the specific precision of a creature whose entire body plan has been optimized for the moment of contact with prey. The sickle claw gripping. The eyes locked on the specific movements of the prey below, the remarkable machinery of a brain that, in its own terms, knew exactly what it was doing. The Cretaceous afternoon is warm, and the air is full of the sounds of an ecosystem at work. The dromaeosaurid is still for a long moment, reading the landscape with the full capacity of its forward-facing eyes and its large olfactory lobes and its carefully developed sense of the patterns that its world makes when all is normal, so that when something departs from the normal pattern, the departure is immediately recognizable. You're doing the same thing in a different context right now. The sleeping brain monitors the patterns of the night. The familiar sounds are filtered as background. The irregular is flagged. The ancient system is working exactly as designed. Rest in that reliability. You have been watched over by this system for every night of your life. It has not failed you yet. The Cretaceous had juveniles. This sounds obvious, but it is worth dwelling on, because the fossil record's bias toward adult animals, larger, denser bones that preserve better, individuals that lived long enough to die in fossilizable conditions, means that juvenile dinosaurs are significantly underrepresented in collections, and the experience of a young dinosaur growing up in the Cretaceous is one of the less-known dimensions of that world. Juvenile dinosaurs grew fast. The bone histology evidence already mentioned shows growth rates that, in some species, rival the fastest growth rates seen in any modern animal. A juvenile T-Rex was adding approximately 2 kilograms of body mass per day during its peak growth phase, a rate of increase that required enormous food intake and produced an animal that went from hatchling to near adult size in perhaps a decade. During this growth phase, the young T-Rex was not the apex predator it would eventually become. It was a mid-sized predator, roughly the size of a large dog at first, growing through the size of a wolf, then a bear, then a horse, and eventually reaching the multi-ton scale of an adult. At each of these sizes, the hunting strategies available to it were different, the prey accessible to it was different, and the social position it occupied in the ecosystem was different. The juvenile T-Rex probably occupied an ecological niche quite different from the adult. Lighter, faster, more agile, capable of pursuing prey that an adult could not chase effectively. This ecological separation between juveniles and adults may have reduced the competition for resources between generations, allowing both to coexist in the same environment without direct competition for the same food supply. The Maiasaura juveniles in the nest, the Troodon hatchlings in the brooded clutch, the young Titanosaur that hatched from its volleyball-sized egg and walked away from the nesting colony within days of hatching. All of these were beginning lives that would, if they were lucky, extend through decades of a Cretaceous world that was full of dangers but also full of opportunities. The juveniles that survived their first year were the ones that went on to reproduce. The ones that did not survive, the majority in the normal dynamics of any population, became food for the predators and scavengers, became part of the cycling of nutrients through the ecosystem, became part of the substrate from which the next generation would grow. In nature's accounting, the death of a juvenile is not a tragedy in any cosmic sense. It is simply the mechanism by which the population is regulated and the resources are allocated. This accounting can be held at the appropriate distance. The individual juvenile's experience of the Cretaceous, whatever form of experience was available to it, was real and specific, and mattered to the extent that any individual experience matters. The population's accounting, in which most juveniles do not reach adulthood, is a statistical reality that does not negate the reality of the individual experience. The young Maiasaura in the nest, being fed by its parent, was experiencing something that was fully real in its own terms. The fact that many of its siblings and cohort mates did not survive their first year does not retroactively diminish the reality of its experience in the nest. Reality is not graded by survival. The brief lives are as real as the long ones. You were a juvenile once. The specific version of you that existed at age 5, at age 10, at age 15. Those versions were as real as the current version, even though they are as inaccessible now as the Cretaceous. They existed. They experienced their version of the world. They are continuous with who you are now in the way that the juvenile T-Rex is continuous with the adult. Not the same, changed by time and growth, but connected by the thread of identity that runs through the changes. The Cretaceous juvenile grew up, or did not. Either way, its brief existence was real, and real in a world that was simultaneously enormous and ordinary. Enormous in scale, ordinary in the sense that every individual in it was simply living its life, doing what the biology of its species required, without any awareness of the larger significance of the world it was in. You're in the same condition, living a life that is, from the inside, ordinary and specific, while from the outside, from the perspective of the deep time this script has been moving through, it is part of something enormous and continuous and old. Both perspectives are true. The inside and the outside are both valid. The ordinary and the enormous are both present in every moment of every life that has ever been lived. The juvenile dinosaur in the Cretaceous nest was in both simultaneously, as you are in both right now. Let that doubleness be restful rather than dizzying. The ordinary is where you live. The enormous is what holds you. Both are here, in this room, in this night, in this breath. Rest in the ordinary, the enormous will take care of itself. Imagine standing at the shore of a sea that no longer exists. The Western Interior Seaway. In the mid to late Cretaceous, a shallow inland sea split the North American continent in two, running from what is now the Gulf of Mexico northward to the Arctic Ocean, dividing the eastern portion of the continent, Appalachia, from the western portion, Laramidia. It was not the deep, cold ocean of the present Atlantic. It was warm, green-tinged with algae, shallow enough in places that you could see the bottom from a boat, even in its central regions, and warm enough that tropical marine life extended far north of where it exists today. The air above this sea was different from any air you have breathed. It was warmer. The late Cretaceous was one of the warmest periods in the past 400 million years, with global temperatures perhaps 8 to 12 degrees Celsius above today's average. There was no ice at the poles. The Arctic was forested. The shallow seas were warm even at depth, a gradual thermal gradient from surface to floor rather than the sharp thermocline that today separates warm surface water from cold deep water. Pterosaurs sailed above the seaway. In the late Cretaceous, pterosaurs had evolved to enormous sizes. Quetzalcoatlus northropii, which lived in the region that is now Texas, had a wingspan of perhaps 10 to 11 meters. It was the largest flying animal that has ever existed. When it was on the ground, it stood roughly as tall as a giraffe. When it flew, it would have created a visual impression somewhere between a very large bird and a small aircraft, something so outside the normal scale of flying things that it would have taken time to process as real. Quetzalcoatlus was probably not a seabird in the way that albatrosses or frigate birds are seabirds. Its skull and neck suggest that it fed more like a modern stork or jabiru, wading or walking through shallow water and picking up prey with its long pointed beak rather than diving or skimming. But it soared above the seaway nonetheless, riding the thermals that rose from warm water, visible from enormous distances, its shadow crossing the surface of the sea in long, slow sweeps. But it is beneath the surface that the real strangeness of the Western Interior Seaway lives. Mosasaurus hoffmanni. The name means Meuse River lizard, after the river in the Netherlands near which the first specimens were found in the late 18th century. It was not a dinosaur. It was a lizard, a marine lizard, closely related to the monitor lizards that still exist today in Australia and Africa and parts of Asia. But it was a lizard of scale and nature so different from its living relatives that it defies easy categorization. At full adult size, it measured between 13 and 17 meters in length. Its head alone was roughly 1.5 meters long, a narrow elongated skull crammed with conical teeth, designed for gripping slippery fish or cephalopods, with a second set of teeth on the palate, pterygoid teeth, that prevented prey from being pushed back out of the mouth once it was seized. Mosasaurus had flippers. Like many lineages of land-going reptiles that return to the sea, as the ancestors of modern dolphins and whales would do much later in the Eocene. The legs of mosasaurs had been modified over millions of years of evolution into broad paddle-like limbs designed for steering rather than weight-bearing. Its tail was long and laterally compressed, developing in the later mosasaurs into a shape with a downward bent tip, very similar to the tail of a modern shark, a tail designed for powerful propulsion through the water column. Its eyes were large, very large, and structured with a sclerotic ring, the ring of small bones found in the eyes of birds and many reptiles, which supports the eye and maintains its shape against the pressure changes of deep diving. The presence and size of the sclerotic ring in mosasaurs suggests that they could compress their eyes appropriately for deep water, and that they could see in significantly reduced light. They were not animals confined to the sunlit shallows. They hunted in the dark water below the thermocline, in the zone where light fails and where their prey, large fish, cephalopods, possibly other marine reptiles, might have hoped the darkness would protect them. Imagine the descent. A large mosasaur, perhaps 12 meters of muscle and scale and purpose, diving below the sunlit surface of the Western Interior Seaway. The light above changes as it descends, the surface receding from bright green-white to a dimmer, cooler blue, then to a blue that is barely distinguishable from grey, then to a darkness that is not quite total, but approaches it. The animal's eyes adjust. pupils widening to fill the iris almost entirely, gathering every available photon. Its body temperature is maintained more effectively than a modern crocodile's by the thermal inertia of its mass, but it is not warm-blooded in the mammalian sense. It is simply very large, and very large animals retain heat better than small ones. At depth, in the near dark, it waits. This is a hunting strategy that works not on speed but on patience. The prey, a large ammonite or a zoophactinous fish, or perhaps one of the smaller, lighter mosasaurs of the same seaway, comes within range. The mosasaur's strike, when it comes, is not preceded by a charge across a long distance. It is a sudden, violent shortening of the gap between two bodies in near darkness, a strike that relies on the precise information gathered by those large, dark-adapted eyes in the seconds before the moment of commitment. The ammonites are worth pausing on. They are perhaps the defining fossil of the Mesozoic seas, the curved coiled shells that are found in rock formations from the Devonian through to the very end of the Cretaceous, at which point they go extinct along with the mosasaurs and so many others. The shell of an ammonite is a logarithmic spiral, the same mathematical form found in nautilus shells today in the arrangement of seeds in a sunflower in the arms of galaxies. The animal that lived inside the shell was a cephalopod, related to the octopuses and squids of today, soft-bodied, tentacled, probably capable of changing colour and pattern as modern cephalopods do. The variety of ammonite forms is extraordinary. Some were the size of a plate, some were the size of a cartwheel. At least one species, Parapuzosia sepenredensis, has been found with a shell diameter of nearly 2.5 meters, the largest ammonite known to science. The animal inside this shell would have been correspondingly massive, a cephalopod so large it challenges the imagination, navigating the warm Cretaceous seas with jet propulsion and tentacles longer than a human body. Now let the seaway grow quieter. Let the pterosaurs above circle away on their thermals, growing smaller and smaller against the pale sky until they are specks, then nothing. Let the surface of the water settle into its long, warm swells. Below the surface, in the dim water, something very large moves slowly. Its shape is indistinct. Its progress is unhurried. The darkness around it is the darkness of 66 million years ago, warm and full of life, the last full expression of the Cretaceous marine world before the asteroid changed everything. There is a particular quality to deep-water darkness that is unlike any other darkness. On land, even on the darkest night, there is some light. Starlight, moonlight, the faint bioluminescence of insects. In shallow water, there is filtered light from above. But in deep water, in the benthic zone well below the photic layer, there is genuine darkness. Not the absence of light, but the complete and absolute non-presence of it. A darkness that is its own thing rather than simply the absence of something else. The creatures that lived in that darkness developed their own means of perception. Bioluminescence, the production of light by living organisms, was present in the Mesozoic seas as it is in today's deep oceans. Some creatures lit themselves up with cold blue-green fire, whether to attract prey, to communicate, or simply as a metabolic side effect of the chemical reactions in their tissues. The darkness of the deep Cretaceous sea was not complete. It was peppered with small lights, moving in the water column, rising and falling with the rhythms of the daily vertical migration that has characterized ocean life for hundreds of millions of years. The mosasaur, hunting in this lit darkness, would have known those lights. It would have learned, through experience or instinct or some combination, which lights meant prey and which lights meant caution. Its world was not simply dark. It was a specific, complex, information-rich darkness that it navigated with the ease of a creature that had been living in it for its entire life. As you're navigating the specific, complex darkness behind your closed eyes right now, the sea that once covered Kansas is gone. The water that was warm and green and full of enormous patient hunters has long since receded, leaving behind limestone and chalk and the fossil evidence of lives lived at enormous scale in a world we can barely imagine. But the darkness is still here. The darkness travels. The darkness is the one constant that connects every world that has ever existed under a night sky. Let it carry you, as it has always carried the sleeping. Let the warm Cretaceous sea move beneath you, gentle and enormous, and let the deep water darkness close over you softly, and let whatever remains of waking consciousness dissolve into something older and quieter than thought. The ammonites deserve more than a passing mention. They are perhaps the most numerous and most diverse of all the macrofossils from the Mesozoic seas, found on every continent in rock formations spanning 240 million years from the Devonian to the very end of the Cretaceous, in sizes ranging from a few millimeters to the 2.5-meter giants already described. The shell of an ammonite is a logarithmic spiral, and the logarithmic spiral is one of those mathematical forms that appears throughout nature with a frequency that suggests it is somehow a fundamental shape, the shape that certain growing processes tend toward when they must increase in size while maintaining the same proportions. The shell of a nautilus, the spiral galaxy, the hurricane as seen from space, the unfurling frond of a fern, the arrangement of seeds in a sunflower, all are logarithmic spirals, all are the same underlying mathematics expressed in different materials. The ammonite's spiral was not decorative, it was functional. The spiral shell provided the cephalopod inside with a buoyancy device, a series of gas-filled chambers called septa, separated by thin walls of calcium carbonate that the animal could fill with gas or liquid to adjust its depth in the water column. By manipulating the gas-to-liquid ratio in the chambers, the ammonite could rise or sink in the water column with minimal energy expenditure, a passive buoyancy system of extraordinary elegance. The soft body of the ammonite, the tentacled, ink-producing, jet-propelling cephalopod that lived in the outer chamber of the spiral, is almost never preserved. We have hundreds of thousands of ammonite shells in museum collections around the world. We have almost no soft tissue impressions of the animal that built those shells. What we infer about ammonite behavior comes from comparisons with the nautilus, the one living relative with a similar shell structure, and from the chemistry of the shells themselves, which preserves information about the water temperature and chemistry the animal lived in. The nautilus is a living fossil in the loosest sense of the term, not unchanged since the Paleozoic, but recognizably similar in basic shell architecture to its ancient relatives. Modern nautiluses are nocturnal, rising from the deep water during the night to feed in the shallower zones and descending again with the dawn. If the ammonites followed similar patterns, and the evidence from their shell chemistry suggests that at least some species underwent daily vertical migrations, then the Cretaceous seas at night were full of ammonites rising from depth, their spiral shells moving upward through the water column in the darkness. The sea at night is not simply the daytime sea with the lights out. The daily vertical migration that characterizes oceanic zooplankton and many small marine organisms is one of the largest animal movements on Earth. Billions of tiny creatures rising each evening from the mesopelagic zone into the surface waters to feed, then descending each morning to avoid the visual predators that hunt in the daylight shallows. The movement of this biomass creates detectable changes in the acoustic properties of the water column, the deep scattering layer, a band of sound-reflecting organisms so dense that early sonar operators mistook it for the sea floor. In the Cretaceous sea, this daily migration was happening on the scale appropriate to that world's enormous biological productivity. The ammonites were part of it, the ichthyosaurs and plesiosaurs were hunting within it, the mosasaurs were cruising through the upper water column where the migrating organisms concentrated. The darkness was not a cessation of activity but a shift in its character, from the sun-driven visual ecology of the day to the chemical and acoustic ecology of the night. Plesiosaurs, we have not spent enough time with the plesiosaurs. The plesiosaurs are in some ways more alien than any other Mesozoic animal. Their body plan, a compact torso, 4 large paddle-like flippers, a long neck and a small head, has no close analogue in any living animal. They evolved from terrestrial reptiles in the early Triassic and were fully marine by the mid-Triassic, and they maintained that marine lifestyle for approximately 130 million years, which is a very long time to be a large marine reptile. The long-necked plesiosaurs, the plesiosauroids, including the famous Elasmosaurus with its neck as long as its entire body, are often assumed to have been surface feeders, using the long neck to reach down into the water to catch fish. But recent biomechanical work suggests this is unlikely. The neck, while long, was not very flexible in the vertical plane, and the head at its end was small with relatively small interlocking teeth. The most plausible feeding strategy, according to the current evidence, was horizontal. The plesiosaur swimming forward and sweeping its long neck through schools of small fish, or soft-bodied invertebrates, the teeth interlocking to trap small prey in a sieve-like fashion. The four-flipper propulsion system of plesiosaurs, already mentioned in the metaphor of underwater flight, has been described by a researcher as essentially the same motion as a bird flying, but through a medium 800 times denser than air. The efficiency of this system, relative to the tail swimming used by fish and most marine mammals, is calculated to be high at low speeds and in highly manoeuvrable situations, consistent with a predator that needed to control its position precisely while hunting in 3 dimensions. Imagine a plesiosaur in the dark Cretaceous sea, not swimming fast, the four-flipper system was not built for speed, but moving with deliberate controlled grace through the dark water. The bioluminescent organisms around it providing just enough light to detect the concentration of small prey animals nearby. The long neck beginning its lateral sweep, the small head moving through the water, the teeth interlocking as they encounter the soft bodies of small organisms. It is a quiet kind of hunting, unhurried, patient. Not the explosive speed of a mosasaur strike, not the aerial plunge of a diving bird, but a slow, deliberate collection, a harvest rather than an ambush. The dark sea held this patience for 130 million years. The plesiosaurs were patient with it, moving through their dark ocean with the specific grace of their improbable body plan, perfectly adapted to a lifestyle and an environment that have not existed on Earth since the Cretaceous ended. The quiet of the deep water is its own kind of rest. Let it be yours. The Western Interior Seaway was not the only body of water that divided or bordered the Mesozoic continents. The Tethys Sea, a great equatorial ocean that existed through most of the Mesozoic, lying between the northern landmass of Laurasia and the southern landmass of Gondwana, was the warm, shallow, biologically rich sea that forms the background to so much of the Mesozoic marine story. The Tethys was ancient even in the Cretaceous. It had been forming since the breakup of Pangaea in the Triassic, as the continent split and the gap between the northern and southern fragments widened into an oceanic basin. By the Cretaceous, it was a warm, shallow, carbonate-rich sea stretching from what is now the Caribbean in the west to what is now Southeast Asia in the east, a sea so large that it encompassed much of the modern Mediterranean, Middle East, and South Asian region. The fossils from the ancient Tethys seafloor are now exposed in mountain ranges that did not exist when the sea did. The Alps, the Himalayas, the Zagros Mountains of Iran, all were formed by the slow collision of the plates that had once been separated by the Tethys, the collision that began in the Eocene and is still continuing today. When you stand on a limestone mountainside in the Alps, or the Himalayas, and see the fossils of marine organisms in the rock beneath your feet, you are standing on the former floor of the Tethys Sea, lifted by the collision of continents to heights that the ancient organisms whose shells you are seeing could not have imagined. The Tethyan limestone that forms much of the rock of southern Europe and the Middle East was formed from the accumulated shells of marine organisms, the same coccolithophore-rich chalk that forms the White Cliffs of England, expressed in different mineral forms depending on the specific chemistry of the deposition environment. In some places, the Tethyan limestone contains the large, complex shells of rudists, enormous, colonial bivalves that built reef structures in the warm Cretaceous Sea and were, functionally, the equivalent of the corals that build today's tropical reefs. The rudist reefs of the Cretaceous were different in structure from coral reefs. The rudists grew not as branching, three-dimensional structures, but as dense clusters of conical or cylindrical shells, packing together into thickets that provided shelter and substrate for hundreds of other species. They were, in their own way, as biologically rich and ecologically complex as the coral reefs that replaced them after the KPG extinction. The KPG extinction killed the rudists entirely, not a single species survived, and the carbonate reef-building niche was left empty until the corals, which had also been severely affected by the extinction, recovered and diversified in the Eocene and Miocene. The rudist limestone that now forms the foundations of ancient cities in the Middle East, the stone of Roman temples, the stone of medieval castles, the stone of houses thousands of years old, is the compressed residue of a Cretaceous reef ecosystem. The cities are built on the Tethyan sea floor. Every stone in every old building in that region is a former marine organism, compacted and mineralized into the durable building material that human civilization has been quarrying and shaping for millennia. This is the geological world in its most literal expression. the deep past is the literal foundation of the human present. Not metaphorically, physically. The stone beneath your feet, in much of Europe and the Middle East and the Indian subcontinent, is Mesozoic marine sediment. The buildings are made of it. The roads are built over it. The soil is derived from it. The Tethys Sea closed 60 million years ago, more or less, as the plates that had once been separated by it finally collided, and the ocean floor was subducted or uplifted into the mountain ranges we know. What was once the deepest, warmest, richest sea of the Mesozoic world is now rock, compressed, mineralized, uplifted, in some places folded into extraordinary complexity by the forces of plate collision, in other places relatively undisturbed, still showing the original horizontal layering of its sedimentary deposition. The marine organisms whose shells built the Tethyan limestone, the ammonites, the belemnites, the rudists, the various foraminifera whose tiny shells constitute the bulk of the fine-grained carbonate, lived and died in that warm sea without any awareness that the world they inhabited was temporary. The Tethys had been there since before they were born, would be there long after they died. The gradual closure, the slow collision of continents that took tens of millions of years, was not an event that any individual organism experienced. It was a geological process, operating at a scale so far above the lifespan of any individual that the individual's life was not measurably affected. In the same way, the processes that shape the large-scale context of your own life are operating at a scale above the individual. The climate is changing on a scale of centuries and millennia. The continents are moving, very slowly, but moving. The mountain ranges are rising and eroding on timescales of millions of years. None of these processes are perceptible in a single human lifetime, and yet all of them are the context within which the individual life is lived. The Tethyan organism in its warm, shallow sea was living inside a geological process without knowing it. As you are living inside geological and historical processes without, in the deepest sense, knowing them either. The knowledge that we have is precious but partial. The frame we can hold is large but not large enough to contain the whole. And that is acceptable. The ammonite did not need to understand plate tectonics to live its ammonite life fully and completely. You do not need to understand the full scale of what contains you to live your own life fully and completely. The context is what it is, and it is holding you whether you understand it or not. The Tethys Sea is gone. The warm, shallow water that covered the future Alps and Himalayas has been replaced by rock, and then by mountains, and then by the complicated human history that has played out on those mountains, and in the valleys between them. The ocean was temporary, everything is temporary in geological time. But the ocean was real while it lasted. The organisms in it were real. The specific lives they lived, the feeding, the reproduction, the daily vertical migrations of the ammonites, the long patient filter feeding of the rudists, were real while they were happening, and the record of their reality is in the rock. Your life is real while it's happening. Tonight is real. The specific quality of this particular night, its sounds, its temperature, its specific darkness, is real, and it is happening, and it will leave its own trace in the record of who you are and what you remember. Let the warm Tethyan sea hold you gently in the memory of its warmth. It is very far back and very far away, and it is nevertheless present in the stone of the world you live in. Everything leaves a trace. Everything was real. The ocean at night is different from the ocean in the day. Not just because the light is different, though the light is radically different. The sunlit surface waters and the dark pelagic zones exchange their character as the daily vertical migration redistributes biomass through the water column, but also because the ocean at night has a different acoustic character, a different temperature profile in the surface layers, a different set of chemical gradients. The bioluminescence of the night ocean is one of the more extraordinary natural phenomena that most people rarely see. On a dark night, far from land, the surface of the ocean can glow with the cold blue-green light of dinoflagellates, microscopic algae that produce light when disturbed by wave action, or the movement of a boat's hull through the water. A wave breaking at night in certain waters will light up with this cold fire, each droplet of water scattering the bioluminescent organisms and leaving a brief phosphorescent trail. The Cretaceous ocean was bioluminescent. The dinoflagellates that produce the most conspicuous modern oceanic bioluminescence were present in the Cretaceous. They are ancient organisms with a long fossil record. The night surface of the western interior seaway, disturbed by wind and by the movements of large marine animals, would have lit up with this cold fire in the same way that modern oceanic surfaces light up. A mosasaur moving through the surface water at night would have been surrounded by its own light, the disturbance of its passage through the bioluminescent layer producing a moving trail of cold blue-green fire that marked its path through the dark sea. The mosasaur could not have seen this light directly, because it was produced behind and around its own body as it moved. But the light was there, visible to any observer watching from the surface or from a slightly different position in the water. The irony of the bioluminescent trail is that it could work against the predator as well as for it. An ambush predator benefits from darkness. A mosasaur producing a glowing trail of bioluminescence as it approached prey was advertising its position in the very medium it was trying to move through invisibly. Whether mosasaurs used the bioluminescence to their advantage, perhaps using it to disorient prey, the sudden flash of light startling fish into momentary immobility, or simply accepted the compromise of being visible in their own approach, is not knowable. The deep ocean of the Cretaceous had its own bioluminescent organisms, the counterparts of the modern deep-sea fish with their luminescent lures, the counterparts of the modern squid with their photophores arranged in patterns specific to species. The deep Cretaceous sea was not dark in the way that a darkroom is dark. It was dark with lights in it, cold, specific, moving lights that encoded information about what was alive and where. There is something about oceanic bioluminescence that has appealed to human imagination since humans first saw it. The cold fire. The light produced by life itself, without heat, without combustion, without any of the mechanisms that produce the light humans are familiar with. It is the oldest light technology. The biochemistry of bioluminescence evolved independently in dozens of different lineages, suggesting that it is both genuinely useful and relatively accessible to evolution. The specific molecules involved in bioluminescence, luciferase enzymes reacting with luciferin substrates in the presence of oxygen, are among the most borrowed tools in modern molecular biology. Luciferase is used as a reporter gene, a marker whose presence can be detected by the light it produces, allowing researchers to track the expression of genes and the location of proteins within living cells. The cold fire of the ancient ocean is now used as a tool to illuminate the interior of living cells. This is a small example of the general principle. The deep past is not separate from the present. The tools developed by evolution over hundreds of millions of years are the same tools that biology uses today in every organism alive, including the organisms doing the research. The bioluminescence that lit up the Cretaceous sea now lights up cell biology laboratories. The ancient chemistry is the modern chemistry. The warm Cretaceous sea is dark above the thermocline tonight. The real night. The night of 66 million years ago that we have been imagining our way into. The bioluminescence is intermittent. A flash here as a mosasaur passes, a steady glow there where a dense concentration of dinoflagellates is being stirred by the slow current. The surface is barely visible from below, a pale, dimly lit ceiling above the dark water. And below, in the deeper dark, the bioluminescent creatures of the deep water are moving in their slow vertical migration, upward toward the surface, as they do every night, carrying their own small lights with them into the shallower water where the food is. The ocean is alive with its own illumination, not enough to see by, not the warm light of a fire or a star, the specific cold light of life doing what life does, converting chemical energy into photons, spending a little of the energy budget on light, for reasons that vary from organism to organism, but that collectively produce a world that is not quite dark even in the deepest night. The room you are in is dark, but somewhere, in the cold deep ocean, small lights are moving. They have always been moving. They were moving in the Cretaceous. They will still be moving when this night is over. The world maintains its own illumination in the ways available to it. Let that be enough. Let the cold fire of the deep sea be a kind of company in the dark, distant, ancient, continuous, real. You're not alone in the dark. Nothing has ever been alone in the dark. The dark has always had its own lights in it. Go back further, past the Cretaceous, past the Jurassic, past the Triassic, to the world before the dinosaurs ruled, the world before the world we have been exploring. 252 million years ago, all of the continents were joined. Pangaea, a name that means all land, was the single supercontinent that covered approximately 1/3 of the Earth's surface area, surrounded by the single ocean, Panthalassa, the all-sea. The geography of this world was so different from today's that a map of it looks like something from a dream. All the familiar coastlines dissolved, all the familiar oceans absent, the landmass gathered into a single vast territory that stretched from pole to pole. The interior of Pangaea was a desert of extraordinary scale. Distance from the ocean means distance from moisture, and the centre of Pangaea was very far indeed from any ocean. Temperatures in the continental interior may have reached 60 degrees Celsius during the Permian summer, higher than any sustained surface temperature recorded in the modern world. The monsoons that drove seasonal rainfall were intense but localised, wetting the coastal margins while the interior baked. This was a world of extremes, a world where the modifying influence of ocean on climate was available only to those lucky enough to live near a coast. In the seas around Pangaea, life was extraordinarily abundant. The Permian seas were the richest marine ecosystems in the history of life, reef systems of enormous extent, built by organisms very different from the corals that build today's reefs, but equally complex in their ecology. Fish of hundreds of species, sharks with proportionally enormous teeth, ammonoid cephalopods in their early diversity, and everywhere, in every ecological niche in the warm shallow seas, the invertebrate life that constitutes the bulk of marine biodiversity. Brachiopods, bryozoans, crinoids, sea urchins, marine worms of extraordinary variety. On land, the dominant large animals were the synapsids, not the dinosaurs, they had not yet evolved, not the mammals, they were still hundreds of millions of years in the future. The synapsids were the ancestors of mammals, but they were not mammals themselves. They ranged from small, rat-like creatures to large, bulky herbivores like moschops, a barrel-chested, heavy-headed animal, perhaps 5 meters long, and to the famous sail-backed predators like Dimetrodon, whose dorsal sail of elongated vertebral spines may have functioned as a thermoregulatory device, capturing sunlight to warm the animal in the morning or releasing heat to cool it in the afternoon. Dimetrodon is often mistaken for a dinosaur. It is not. It lived 50 million years before the first dinosaur evolved, and it is, in terms of evolutionary relationship, more closely related to you than to any dinosaur. The lineage that led from Dimetrodon and its synapsid relatives eventually produced the therapsids, then the cynodonts, then the first true mammals, a lineage that wound through catastrophe and recovery over 200 million years to arrive, eventually, at the creatures that have been telling each other stories since the Pleistocene. The synapsid world of the Permian was rich and varied, and had been developing in its own direction for 50 million years when the Permian-Triassic extinction event began. And the Permian-Triassic extinction was, by every measure available to science, the worst thing that has ever happened to life on Earth. 96% of all marine species, 70% of all terrestrial vertebrate species, the reef systems that had taken tens of millions of years to develop, gone. The rich synapsid diversity of the Permian land, reduced to a handful of survivor lineages, the Great Permian Sea, with its extraordinary invertebrate life, emptied to a degree that makes the KP extinction, devastating as it was, look modest by comparison. The cause was the Siberian traps. A volcanic province in what is now Siberia erupted with a duration and volume that dwarf any volcanic event in recorded human history. For tens of thousands of years, flows of basaltic lava covered an area roughly the size of the continental United States in rock up to 3 kilometers thick. The volcanic gases released by this eruption, carbon dioxide, sulfur dioxide, hydrogen sulfide, accumulated in the atmosphere and the oceans at rates and concentrations that ecosystems had no means of adapting to. The oceans acidified, the atmosphere warmed, the ozone layer was compromised by chemical reactions involving the volcanic halogens. Life on land and in the sea was exposed simultaneously to a suite of stresses from which it had no evolutionary experience of escape. The silence after was profound, not total silence. Some things survived, and survival is never truly silent. but the ecological silence of a world whose complexity has been suddenly and drastically reduced. Walk along the shore of the early Triassic Sea, 2 million years after the extinction peak, and what you find is a world that looks like a world recovering from something enormous. Stromatolites, those simple, layered bacterial mats that had been among the most primitive forms of life since the Archean, flourished again in the empty Triassic seas as they had last flourished in the Cambrian, before complex life had been diverse enough to graze them into minority. The presence of stromatolites in the early Triassic rock record is itself a kind of silence. They grew where nothing more complex could yet grow. But life returned. It always does. Within 10 million years, a span that sounds long in human terms but is barely a blink in geological time, the oceans were diversifying again. New reef-building organisms had evolved. New fish lineages were filling the niches left empty by the Permian extinctions. On land, the surviving synapsids were recovering, diversifying, beginning the long journey toward the mammals that their lineage would eventually produce. And in the margins of the recovering world, small, lightly built, fast-moving archosaurs were experimenting with new body plans. The archosaurs, the group that includes the ancestors of both crocodilians and dinosaurs, diversified rapidly in the early and middle Triassic, filling the ecological vacuum left by the extinction. Among them were the first dinosaurs, small, bipedal, agile animals that appeared in the middle Triassic and initially occupied modest ecological niches as small predators or omnivores, Eoraptor, Herrerasaurus, Coelophysis. Animals that would, in their own terms, have seemed unremarkable. Medium-small predators in a world that still had plenty of competition from other archosaur lineages. Only gradually, over tens of millions of years, did the dinosaurs come to dominate. The process was not a single conquest, but a slow, incremental taking of ground, driven in part by the other archosaur lineages gradually declining, and in part by the dinosaurs' own evolutionary advantages, a more upright posture that allowed more efficient locomotion, a respiratory system connected to air sacs that allowed more efficient oxygen exchange, and possibly some degree of endothermy, metabolic heat production, that allowed them to remain active in conditions that slowed their competition. The world was patient with its own recovery. It did not rush the dinosaurs to prominence. It allowed the conditions to develop slowly, over geological time, until the animals that had survived the worst extinction in Earth history had given rise to the animals that would define the next 165 million years. This is the deep pattern of Earth's history. Catastrophe is followed by silence. Silence is followed by recovery. Recovery is followed by new complexity. The complexity eventually reaches a level where it is again vulnerable to catastrophe, and the cycle continues. It is not a hopeful pattern exactly if you are inside any particular catastrophe, but viewed from the geological distance of 250 million years, it is something else. It is a pattern that suggests the persistence of life as a fundamental feature of the world rather than an accidental one. Life does not merely survive catastrophe, it uses catastrophe. It fills the space that catastrophe creates. It finds, in the emptied world, the room it needs to become something new. The empty Triassic shore with its bacterial mats and its recovering seas. The empty sky, from which the Permian pterosaur predecessors had not yet risen. The empty forests, where dinosaurs had not yet walked. And then, slowly, life filling it back in. Your breath is slow now. The world outside your window, with all its busyness and noise, is resting in its own way. The Triassic silence is not here. It is 250 million years behind you. But its lesson is here, that recovery is always possible, that the most complete devastation eventually gives way to something new, that patience is, in the geological sense, the most reliable virtue the universe possesses. Sleep well in that knowledge. The world has survived much worse than tonight. The Triassic recovery was not uniform. It happened at different rates in different regions, shaped by the specific geography of a single supercontinent and the particular way that the volcanic catastrophe had affected different parts of the world. The ocean floor recovered before the land, as it typically does, because the ocean has more thermal stability and the deep ocean retains nutrients even when the surface layers are disrupted. The land recovered fastest in the regions that had escaped the worst of the volcanic winter, in the far south and north where the effects of the Siberian eruptions were most attenuated, In some Triassic formations, the rocks show a pattern called the disaster fauna, a characteristic set of species that appear immediately after the extinction and dominate the early recovery period. These species share certain traits: generalist diets, rapid reproduction, tolerance for a wide range of environmental conditions. They are essentially the weedy species of the Triassic, the ecological equivalents of dandelions and rats and pigeons, the animals that do well in disturbed and simplified ecosystems. Lystrosaurus was the most successful of the disaster fauna. A small to medium synapsid herbivore with a robust pig-like body, a short face, and 2 small tusks, it has been found in early Triassic deposits on every southern continent: Antarctica, India, South Africa, China. Its ubiquity suggests that it survived the extinction event with a level of success that almost no other large vertebrate achieved, and that it then spread rapidly through the recovering landscape, filling the ecological vacuum left by the extinction. For a while, for perhaps 1 million years in some estimates, Lystrosaurus may have constituted more than 90% of the large vertebrate fauna in parts of the recovering world. Almost every large vertebrate in certain regions of the early Triassic land was Lystrosaurus. This is an ecological state without parallel in the modern world, a world where a single species so dominates the large vertebrate fauna that every other large vertebrate is a rarity. The gradual diversification away from this Lystrosaurus monoculture is one of the compelling stories of the Triassic. Over millions of years, the surviving archosaur lineages diversified and increased in size and ecological diversity. The surviving synapsid lineages, the therapsids that would eventually give rise to mammals, also diversified, producing new forms that occupied new niches. And gradually, the Triassic world moved from its simplified disaster fauna toward the more complex, more diverse ecological community that would eventually become the Jurassic world. The first dinosaurs appeared in this context, not as conquerors, but as one group among many, finding their place in a recovering world that had room for new experiments. Eoraptor from Argentina was perhaps 2 meters long and roughly the size of a large dog, small, lightly built, fast, probably omnivorous or carnivorous. It shares the Triassic landscape with other archosaurs, other small predators, other experiments in body plan and ecological strategy. There is nothing about Eoraptor that would lead you to predict that its lineage would eventually produce Patagotitan. There is nothing in the small, fast, generalist early Triassic dinosaurs that announces the future they contain. This is, of course, a universal feature of evolutionary trajectories. The future is not visible in the present. Lystrosaurus, at the height of its Triassic abundance, showed no sign of impending decline. The small feathered Cretaceous dinosaurs showed no sign of being the lineage that would survive the asteroid and produce 10,000 bird species. The future is always opaque in the present. This is not a flaw in the system, it is the system. Evolution works by variation and selection in the specific conditions of the specific present, with no access to what the future will require. Every lineage is adapting to now, not to then. The ones that happen to be adapted to the then that arrives are the ones that persist. The ones that were adapted to the now that ends do not. There is something clarifying about this perspective. The anxiety that comes from trying to prepare for futures that cannot be known, from trying to control outcomes that depend on conditions not yet present, is the anxiety of an organism trying to do something that evolution has never solved, predicting the future well enough to prepare for it. The Cretaceous dinosaurs could not prepare for the asteroid. The Permian fauna could not prepare for the Siberian traps. The best that any lineage has ever done is be flexible enough, generalist enough, adaptable enough to respond to whatever arrives. The early mammals were not prepared for their post-extinction dominance. They were prepared for the Cretaceous, for the small, nocturnal, insect-eating niche they had occupied for 100 million years. When the extinction cleared the large animal niches, they were flexible enough to move into them. They were not the most specialized animals in the Cretaceous ecosystem. They were among the least specialized, and that turned out to be exactly what the post-extinction world required. The world tonight is asking you, as it always does, to simply be flexible enough and generalist enough and present enough to respond to whatever arrives. Not to predict the future, not to control the uncontrollable, just to be here, available, in the present. The Triassic recovery took 10 million years. You have until morning. The scale is different, but the principle is the same. Rest now, so that whatever arrives, you are ready. The ancient world recovered. The modern world was built on that recovery. Tonight is part of that building, one quiet night at a time. The relationship between plants and the animals that ate them in the Mesozoic was a long, slow negotiation, a co-evolutionary arms race in which the plants developed defences and the herbivores developed counter-defences, each driving the other's evolution in directions that neither was choosing. The conifers and ferns that dominated the Mesozoic landscape were not passive victims of herbivory. They had physical and chemical defences, tough, thick leaves that were harder to process than the soft, nutritious leaves of later flowering plants, resinous compounds in the wood, and bark that were toxic or distasteful to many organisms, silica deposits in the cell walls of some species that increased the abrasive quality of the foliage. These defences were effective against small insects and against the less specialised herbivores. They were less effective against the large, specialised herbivores that the Mesozoic eventually produced. The sauropods got around plant defences partly through scale. If you can eat enough bulk, the relative proportion of defensive compounds in your intake is diluted, and partly through gut specialisation. The long gut of a large sauropod, processing tons of plant material daily with the assistance of gastroliths, and a large, complex microbial community in the fermentation chambers, could detoxify compounds that would be problematic for smaller, simpler digestive systems. The hadrosaurs took a different approach, the dental battery already described, which could process tougher plant material than any other herbivore of the Cretaceous. Hadrosaurs could eat the coarser, more silica-rich vegetation that sauropods might have found less accessible, the reed-like plants, the tougher ferns, the coarser horsetails that grew in the wetter environments of the late Cretaceous. By accessing plant material that other herbivores could not efficiently process, hadrosaurs carved out an ecological niche that was not simply a subdivision of an existing niche, but a genuine extension of the range of plant material available to Cretaceous herbivores. The ceratopsians, with their parrot-like beaks, were adapted to yet another plant resource, the tough, fibrous, possibly chemically defended vegetation of the drier upland environments of the late Cretaceous. Triceratops and its relatives lived in habitats that the hadrosaurs may have found less accessible, feeding on plant material that required the specific combination of beak power and dental battery grinding that the ceratopsian skull provided. The distribution of these different herbivore types across the late Cretaceous landscape of North America reflects the partitioning of plant resources by different specializations, the ecological equivalent of different tools for different materials. The sauropods ate high and in bulk. The hadrosaurs processed the medium-height, higher-quality vegetation. The ceratopsians worked the tough, low vegetation of the drier areas. The small herbivores, the hypsilophodonts, the ankylosaurs browsing at low heights, picked over the leavings and the specialized microhabitats. The plants, meanwhile, were evolving in response to this pressure. The flowering plants, the angiosperms, that appeared in the early Cretaceous and diversified rapidly through the late Cretaceous, were partly a response to the enormous herbivory pressure of the Mesozoic. Flowers and fruits are, in part, a strategy for directing animal interactions, attracting pollinators with flowers, attracting seed dispersers with fruits, but they also represent a shift in the cost of herbivory. An animal that eats a fruit and deposits the seed elsewhere has been co-opted into the plant's reproductive strategy, rather than simply extracting resources from it. The relationship between plant and animal, in the case of fruit eating, is mutualistic rather than purely exploitative. The Cretaceous saw the early stages of this transition, the first flowers, the first fruit-like structures, the first pollinators that were beginning to co-evolve with flowering plants. The mammals that survived the KPG extinction were, in many lineages, fruit-eaters, seed-eaters, generalist foragers that benefited from the early diversification of flowering plants. The very success of the mammals in the post-extinction world was partly enabled by the evolutionary work that the angiosperms had done during the Cretaceous. This is one of the most remarkable facts in the history of life. The animals that replaced the dinosaurs as the dominant terrestrial vertebrates were enabled, in part, by plants that had been evolving under the pressure of dinosaur herbivory. The dinosaurs did not simply occupy the Cretaceous world, they shaped it in ways that determined what came after. The angiosperms' diversification under herbivory pressure created the resource base that the mammals would exploit. The dinosaurs made the world that replaced them. This kind of unintentional legacy is everywhere in the history of life. The cyanobacteria that produced the Great Oxygenation Event 2.5 billion years ago, poisoning the atmosphere with oxygen as a waste product of their photosynthesis, made the world safe for oxygen-breathing life. They did not intend to. They were simply doing what they did, and what they did changed everything. Every organism that has ever lived has left some kind of unintentional legacy. The oxygen you're breathing right now was produced by cyanobacteria and their descendants over billions of years. The fruit you ate yesterday was produced by a plant whose ancestors co-evolved with dinosaurs and their mammalian successors. The soil your food grew in is partly the product of the activities of earthworms and soil microorganisms, whose ancestors were already doing this work in the Carboniferous. You are the beneficiary of legacies so old and so numerous that cataloguing them would take more time than the universe has existed. Every breath is an inheritance. Every meal is an inheritance. The body that is resting now is the current expression of 4 billion years of inherited solutions to the problem of being alive. The plants are outside your window right now, doing their quiet work in the dark, not photosynthesizing that requires light, but respiring, cycling nutrients, maintaining the living systems that will resume full activity in the morning. The world outside is not asleep in the way that you are asleep. It is doing what it does in the dark, what it has always done in the dark, what it will continue to do in the dark long after tonight is over. Let the plants do their work, let the world do what it does. You do not need to help it. You never have. It has been managing without your assistance since long before you existed, and it will continue after. Rest in that knowledge. The world does not require your supervision tonight. The oxygen content of the Triassic atmosphere was lower than today's, a consequence of the Permian extinction and the disruption of the global carbon cycle by the Siberian Traps volcanism. Current estimates suggest that Triassic atmospheric oxygen may have been as low as 16% compared to the modern 21%. This relatively low oxygen environment would have had significant effects on the physiology of the animals living in it. Low oxygen favours animals with efficient respiratory systems that can extract more oxygen from each breath, or that can maintain activity on less oxygen per unit of body mass. The archosaurs, the group that eventually produced both the dinosaurs and the crocodilians, appear to have had more efficient respiratory systems than their contemporaries. The air sac system that characterises modern birds, and that was present in at least some dinosaur lineages, may have evolved partly as a response to the low oxygen conditions of the Triassic. If the air sac system gave early archosaurs a respiratory advantage in the low oxygen Triassic, it may partly explain the eventual success of the dinosaurs relative to other large vertebrate groups of the time. Not the only explanation. The Triassic was complicated, and the rise of dinosaurs to dominance was a gradual process with multiple contributing factors. But a respiratory advantage in a low-oxygen world is a genuine competitive advantage, and its effects would have compounded over the generations. The Jurassic and Cretaceous atmosphere had higher oxygen levels than the Triassic, possibly as high as 25 or 30% in the late Carboniferous, declining somewhat through the Mesozoic. Higher atmospheric oxygen supports larger animals. The maximum possible body size is constrained by the efficiency of oxygen delivery to tissues, and higher oxygen availability relaxes that constraint. The enormous size of the largest Mesozoic animals may have been enabled, in part, by the oxygen-rich Mesozoic atmosphere. The air you are breathing tonight contains 21% oxygen, the same concentration that the post-Miocene atmosphere has maintained, more or less, as the result of the balance between photosynthesis and respiration in the global biosphere. The specific oxygen concentration of the air is the product of billions of years of biological activity. Photosynthesis producing oxygen, respiration consuming it, the net balance settling at approximately 21% as the various biological processes reach their current equilibrium. Your lungs are adapted for 21% oxygen. The hemoglobin in your blood binds oxygen at the partial pressures produced by 21% atmospheric oxygen. The mitochondria in your cells are calibrated for the oxygen concentrations that 21% provides. You are, in your respiratory physiology, precisely matched to the current atmosphere, the product of evolutionary adaptation over 66 million years of post-extinction mammalian evolution, all of which has taken place in a world with approximately 21% atmospheric oxygen. If you were transported to the Triassic and stood in its 16% oxygen air, you would notice the difference. Not dramatically. 16% is not dangerous for a healthy human at sea level, but it is lower than your optimal, and sustained activity would be more difficult. The margins between adequate and inadequate narrower. The early archosaurs, with their air sac systems, managed in that atmosphere more effectively than you would. The specific composition of the air is a form of inheritance, like the rock below and the light above. The 21% oxygen in the air you are breathing was produced by the photosynthesis of plants and algae over hundreds of millions of years. The specific molecules of oxygen entering your lungs right now may have been released by a plant on the other side of the world today, or they may have been cycling through the atmosphere for centuries, passing through other lungs, other bodies, other metabolisms before arriving here. The oxygen is very old. Its current chemical form is new. It was released as a gas within the past few years or decades. Before that it was bound in carbon dioxide or water or organic molecules. But the atoms themselves, the oxygen nuclei with their 8 protons and 8 neutrons, were forged in a massive star that died before the solar system formed. The oxygen is stellar debris. You are breathing the residue of stellar nuclear synthesis. This is the chemical version of the deep time perspective, not the temporal scale of geological time, which is vast, but the nuclear scale of cosmic time, which is vaster. The atoms in your body are cosmically old. The universe itself is their context. You are a temporary arrangement of material whose history extends back to the very beginning of what we call time. Hold that lightly. Not as a source of anxiety, the cosmic scale is not a threat to the human scale, but as a kind of companionship. Everything that exists is in the same condition, made of old material, arranged in temporary forms, doing what the specific arrangement allows for the duration of its existence. The Triassic atmosphere was thin on oxygen, and the early archosaurs moved through it with the specific efficiency of creatures adapted to exactly those conditions. The Cretaceous atmosphere was richer, and the enormous bodies of the Mesozoic were possible because of it. The current atmosphere is what it is, and you are breathing it, in this specific room, in this specific night. The breath is the most continuous act of being alive. From the first breath to the last it has been happening. This exchange of gases with the atmosphere, this ancient cellular bargain between the body and the air. Feel it now, slow and easy, the ancient air entering, the ancient metabolism doing its ancient work, the night continuing its reliable passage toward morning. The Triassic recovery is far behind you, the Cretaceous is far behind you, you are in the present, breathing the present air, resting in the present dark. This is exactly where you should be. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this every week, and there will always be another world waiting for you when you return. In the forests of northeastern China, 130 million years ago, a morning is beginning. The light comes in at a low angle, filtered through the dense canopy of a forest that contains trees we would recognize, conifers, some of the early flowering plants, ferns in the undergrowth, but arranged in proportions and densities that are slightly wrong by any modern standard. The sky above the canopy is a particular shade of early morning blue that has not changed in 130 million years. Colour is a physical property of light and atmosphere, and the atmosphere of the early Cretaceous was not so different from today's that the sky would have looked foreign. In the trees, things are moving. Not the large theropods of the late Cretaceous, those came later. In the early Cretaceous forests of the Yixian Formation, the theropods are small, many of them are feathered, some of them have 4 wings rather than 2. And the line between dinosaur and bird is, in this forest, not a line at all but a gradient, a spectrum of forms that resist easy categorization. Microraptor Guy settles on a branch. It weighs approximately 1 kilogram. Its 4 wings, 2 on the arms, 2 on the long hind legs, are fully feathered with long asymmetrical flight feathers similar in structure to those of modern birds. The feathers on its body are iridescent black in the manner established by the melanosome evidence, a deep, glossy darkness that shifts between blue and green in the light. It uses its 4 wings not for powered flight, as birds use their 2 wings, but for gliding, extending all 4 limbs to create a biplane-like configuration that allows it to travel between trees with a controlled downward trajectory, and a horizontal distance that far exceeds what a simple leap could achieve. It is watching the forest floor, its forward-facing eyes, already in this early Cretaceous form, showing the forward placement and relative size associated with predatory vision, track a small lizard moving through the leaf litter below. The lizard stops. Microraptor's eyes fix. There is a pause that is identical in quality to the pause of a modern hawk above a field, the moment before commitment, the gathering of information that must be translated in a fraction of a second into a trajectory and a speed and an angle. Then the glide, a controlled fall from the branch, the four wings extended and angled to manage the descent, the body streamlined, the clawed feet coming forward at the end of the glide to seize the lizard in the same motion that carries the animal to the ground. What you have just watched is a behaviour that connects across 130 million years to the peregrine falcon diving above a city centre, the sparrowhawk banking through a garden, the kestrel hovering above a motorway verge. The specific mechanics are different. The underlying logic, a feathered, forward-eyed theropod using its modified forelimbs to close the gap between itself and prey, is the same logic that has been refined by evolution ever since Microraptor was practicing it in an early Cretaceous forest. The feather itself is worth a moment of slow attention. A feather is an extraordinarily complex structure. The central shaft, the rachis, is hollow, with a cross-sectional geometry that provides maximum rigidity at minimum weight. From the rachis extend barbs, and from the barbs extend barbules, and from the barbules extend microscopic hooks called barbicels that interlock with the barbicels of adjacent barbules to create the smooth, continuous vein of the feather. This interlocking hook system is precisely what allows a bird to preen a damaged feather back to functionality. The hooks can be re-engaged, the vein restored, without the feather needing to be shed and replaced. This structure evolved not all at once, but incrementally, over tens of millions of years. The earliest feather-like structures in the fossil record are simple filaments, hair-like protrusions from the skin with no barbules, no interlocking hooks, no flight function. These filaments are found in remarkably early dinosaurs. They probably served a thermoregulatory function first, insulation, the way mammal hair insulates, before they were co-opted by evolution for display, then for aerodynamic purposes. The sequence is reversed from what intuition might suggest. Flight feathers were not the beginning of feathers. They were the end of a long developmental story that began with insulation and passed through display before it arrived at flight. The beautiful asymmetrical flight feather of a modern barn owl with its serrated leading edge for silent flight is the product of 150 million years of refinement from a simple filament on the skin of a small Triassic theropod that was simply trying to stay warm. There is something in that sequence, insulation, then display, then flight, that has a quality almost like narrative. The first feathers kept an animal warm. The next generation of feathers also made it visible, recognizable, beautiful in a biological sense, an individual with a visual identity that could be read by other members of its species. And the final expression of the lineage made it capable of moving through a dimension that no land animal had previously occupied, from warmth to identity to freedom, over the course of 150 million years. In the Ixian forest, other feathered forms move through the trees. Sinornithosaurus, roughly the size of a crow, with its long arms and curved claws and a body covering of fine, hair-like feathers. Confucius ornis, the earliest known bird with a true toothless beak, its body already so bird-like that if you found it in a modern forest without knowing its age, you might not immediately recognize it as remarkable. Caudipteryx, a larger form, about the size of a peacock, with a fan of display feathers on its tail, feathers that were almost certainly not used for flight but for the same purposes that peacock tails are used for today. Courtship, recognition, the constant negotiation of social status that characterizes group living animals. The diversity of forms in this single forest suggests a world in which the category of bird was not yet established, in which the evolutionary space between feathered dinosaur and true bird was occupied by dozens of experiments, each one a different answer to the question of how a small feathered tree-living theropod might best go about the business of surviving. Most of those experiments ended. Most of the Ixian forms left no direct descendants in the modern world. The asteroid, and the extinction that preceded and followed it in various forms, pruned the extraordinary diversity of early birds down to a single surviving lineage, the neornithins, from which all modern birds descend. But here is the astonishing thing. From that single surviving lineage, 10,000 species have emerged. 10,000 different answers developed over 66 million years of recovery and diversification to the question of how a small, feathered, warm-blooded theropod might occupy the world. Penguins and hummingbirds and albatrosses and ostriches and birds of paradise and barn owls and ravens. The full, extraordinary variety of the modern bird world. All of it descended from a few small, ground-dwelling, seed-eating birds that survived the asteroid winter in whatever way small, desperate things survive winters. When you next see a bird, a crow at a rubbish bin, a pigeon on a window ledge, a sparrow in a garden hedge, you are looking at the living end of a lineage 165 million years long. You are looking at the only living dinosaurs, the only ones that made it through, the only ones still flying. The Ixian forest is quiet now, the early morning light strengthening. Microraptor has made its catch, and is somewhere in the canopy, dealing with the lizard in the systematic way of predatory birds. The other feathered forms are going about their business, foraging, displaying, resting in the warm patches of sunlight that fall through gaps in the canopy. Above them all in the warming air a feather falls. A single iridescent black feather from Microraptor's glossy wing, drifting down through the layers of the forest in the slow spiral that falling feathers always make, as if they have nowhere urgent to be, as if the fall itself is sufficient occupation. It settles on the forest floor, the forest receives it without comment. 130 million years later, something very like that feather is still falling, still catching the light, still being received by the world without comment. This is how the ancient night carries you, like a feather drifting down. The origin of flight itself, the transition from a ground-running or tree-living theropod to a feathered animal capable of sustained aerial locomotion, is one of the great unsolved problems of paleontology, and its partial solution is one of the most interesting stories in the science. Two competing hypotheses have dominated the debate for over a century. The ground-up hypothesis proposes that flight evolved in small, ground-running theropods that developed longer and longer forelimbs for catching prey, and that the aerodynamic properties of proto-feathered forelimbs were gradually improved by selection until true flight was achieved. The trees-down hypothesis proposes that the ancestors of birds were tree-living animals that glided first and then evolved powered flight from the glide using trees as the initial platform from which to launch. The evidence from the Ixian Formation and other sites has complicated both hypotheses. Microraptor, with its 4 wings, was almost certainly a tree-living glider, the trees-down scenario. But Microraptor is not on the direct line to modern birds. It is a side branch, an experiment that went extinct without leaving bird descendants. The direct ancestors of birds may have used a different route to flight. Recent work on the wing-stroke mechanics of living birds and comparisons with the anatomy of early bird fossils suggests that powered flight may have evolved multiple times in the dinosaur lineage, and that what we call birds may be the one lineage in which all the necessary features, the wishbone, the keeled sternum for flight muscle attachment, the specific wing proportions, came together in a single body plan that allowed sustained powered flight. This multiplicity is itself significant. Flight was not a single invention, a single breakthrough, a single moment when the first bird left the ground and everything changed. It was a repeated experiment, tried in different forms by different lineages, most of which failed in the long run, but each of which added something to the understanding of the problem that natural selection was, in its blind and patient way, working on. Archaeopteryx, the famous first bird or proto-bird found in the Solnhofen limestone of Bavaria, is probably not on the direct line to modern birds. It is another experiment, close to the main line but not exactly on it. Its feathers are fully developed flight feathers. Its wishbone is present, but its brain is not fully bird-brained. It lacks the enlarged visual cortex and cerebellum found in modern birds. It was not doing everything that modern birds do, but it was doing something. It was at a point in the spectrum between non-flying feathered dinosaur and flying feathered dinosaur that was close enough to the latter that the distinction is largely a matter of definition. The Solnhofen limestone in which Archaeopteryx was preserved is itself a remarkable thing. It was formed in shallow lagoons in the late Jurassic, the fine-grained carbonate sediment preserving organisms in extraordinary detail. Not just Archaeopteryx, but hundreds of other species, including horseshoe crabs, fish, small pterosaurs and invertebrates that give us a detailed picture of a specific marine environment 150 million years ago. The water in these lagoons was probably hypersaline, too salty for most life to survive, which prevented bacterial decomposition and allowed the organisms that fell into the water to be preserved as they settled into the fine sediment. The first Archaeopteryx specimen was found in 1861, 2 years after Darwin published On the Origin of Species. The timing felt, to the scientists of the era, almost providential. Here was exactly the kind of transitional form between reptile and bird that Darwin's theory predicted should exist. The specimen was purchased by the Natural History Museum in London, where it remains today, preserved in its Solnhofen limestone slab in a temperature-controlled storage environment, the finest feather impressions visible in the pale stone as clearly as the day they were found. 160 years after its discovery, Archaeopteryx is still yielding information. High-energy X-ray scanning of the specimens has revealed bone structure invisible to ordinary examination. Chemical analysis has extracted information about the original composition of the feathers. Each new technique finds something that previous techniques missed. The bird that's outside your window right now, or that will be when morning comes, is the heir of everything the Yixian forest was experimenting with, everything the Solnhofen lagoon preserved, everything the asteroid Winter tested to breaking point. It is a compact expression of 165 million years of evolutionary history, carrying in its hollow bones and its downy feathers and its extraordinary navigation abilities the compressed legacy of every feathered theropod that came before it. In the morning when you hear it, you will be hearing the end of a very long story. The ending is not quiet. It never has been. The birds have always been loud, from the earliest troodontid vocalizing in its Cretaceous forest to the blackbird that announces the suburban dawn. They have things to say, territory to declare, the world to announce their presence in. But for now, in the dark, the birds are sleeping. The nest is warm, the feathers are folded, the ancient machinery of the sleeping brain is processing the day just past and preparing for the day to come. As you are, as everything is, in the long dark before the morning. The bird that survived the asteroid Winter was small. This is worth dwelling on. The largest neornithine birds alive today, ostriches, emus, rheas, cassowaries, all evolved after the extinction event in the Paleogene, from ancestors that were small enough to pass through the bottleneck of the impact winter. The giant flightless birds, the enormous flying birds of the Eocene and Miocene, the eagles with wingspans of 3 meters, all of them are post-extinction phenomena, evolutionary responses to the empty large animal niches of the recovering world. The ancestor of all living birds was something like a small ground-feeding or generalist-feeding bird, probably capable of flight, probably eating seeds and invertebrates, probably nesting on the ground or in low vegetation. Nothing about this ancestor suggests the full diversity of what it would eventually produce. Nothing about a small, drab, seed-eating survivor of an extinction event suggests albatrosses, or birds of paradise, or penguins, or hummingbirds. The hummingbird deserves a moment of specific attention because it is, in its own way, as improbable as any Mesozoic animal. The ruby-throated hummingbird of eastern North America weighs approximately 3 grams. It beats its wings between 50 and 80 times per second. Its heart, at peak activity during hovering flight, beats at over 1,200 beats per minute. It can fly backwards. It can hover with a precision that allows it to insert its long curved bill into a flower with millimetre accuracy while both the bird and the flower are moving in the wind. The metabolic rate of a hovering hummingbird is the highest of any warm-blooded animal measured. Weight for weight, a hovering hummingbird consumes more oxygen per second than a running cheetah. It sustains this metabolic rate for the duration of each hovering bout, typically a few seconds to a minute, and then rests between foraging bouts, dropping its metabolic rate to a fraction of the hovering level. During cold nights, some hummingbirds enter a state of torpor, dropping their body temperature and heart rate dramatically to conserve the energy reserves that their tiny bodies cannot maintain through the cold hours at normal metabolic activity. The torpor of a hummingbird is not sleep. It is something deeper, a physiological shutdown so extreme that the animal's body temperature may drop to near ambient, and its heart rate drops from 1200 to fewer than 50 beats per minute. The animal in torpor is, in a functional sense, barely alive. It cannot respond to stimulation as a sleeping animal can. It cannot maintain its usual thermoregulation. It is entirely dependent on the temperature of its environment not dropping below the critical threshold. Every morning that a hummingbird that entered torpor the previous night successfully rouses is a small victory of biology over the thermodynamics of the night. The warming from torpor is accomplished by the generation of metabolic heat from the reserves accumulated during the previous day's foraging. The process takes 30 minutes or more, during which the bird is vulnerable, capable of flight, still too cold for full function, dependent on the morning warmth to complete the process of waking. This vulnerability, this daily gamble with the night, is the price of the hummingbird's extraordinary daytime performance. The metabolic rate that allows hovering precision and the reflexes that allow aerobatic flight require the energy reserves that can only be built in the brief foraging windows of a short summer day. The torpor is what makes the reserves last through the night. The two states, the extraordinary activity of the day and the near-death stillness of the night, are two poles of the same strategy. Your sleep is not torpor. You maintain your body temperature through the night, your heart rate drops modestly rather than catastrophically, and you can wake at will. You're not as close to the edge as the hummingbird, but your sleep is on the same continuum. It is the state that allows the active day to be sustainable, the restoration that makes the next day's activity possible. The hummingbird in torpor and you in sleep are both doing the thing that complex metabolism requires, the periodic rest that allows the systems to consolidate, restore, and prepare. The hummingbird's night is more dramatic, closer to the edge, more vulnerable, more dependent on the specific conditions of the morning. Your night is gentler, warmer, safer, but both nights are the same kind of thing, the necessary other half of the cycle that makes the day possible. The Cretaceous feathered dinosaurs that gave rise to the hummingbird's ancestors were sleeping in their own ways 66 million years before the first hummingbird evolved. The specific architecture of hummingbird torpor is a post-extinction development. The specific pressures of small size and high metabolism that produce torpor were not present in the Cretaceous ancestors, but the underlying capacity for sleep, for rest, for the periodic withdrawal from full activity, that was there. The lineage that produced the hummingbird passed through the asteroid winter. The specific ancestor that passed through was probably small, probably seed-eating, probably not yet capable of the extraordinary hovering flight that defines hummingbirds today. But it was a bird, and it had the bird's capacity for sleep, and it used that capacity to survive the long, cold nights of the impact winter, when every calorie was precious, and every morning's survival was not guaranteed. You're also passing through a night that requires something of you, not the life or death night of the impact winter, not the metabolic extremity of hummingbird torpor, a gentler night, a safer night, a night that asks only that you allow it to do what it does, restore the body, consolidate the mind, prepare the systems for another day. The birds that survived the asteroid winter survived it one night at a time, one morning at a time, the day returning, the warmth coming back, the foraging resuming, the slow rebuilding of the reserves that would get them through the next night. You're making it through this night in the same incremental way, one breath at a time, one slow heartbeat at a time, the body doing its work without your supervision, the morning already, at some imperceptible level, on its way. The eye of a bird is, relative to its skull, proportionally larger than the eye of almost any other vertebrate. A European starling has eyes that, relative to head size, are larger than human eyes relative to head size. An owl has eyes so large that they cannot move in their sockets. The owl must turn its entire head to shift its gaze. The visual system of birds is, in proportion to their body size, among the most developed of any vertebrate group. This visual emphasis is a Mesozoic inheritance. The theropod dinosaurs from which birds descended were visually oriented predators with forward-facing eyes and large optic lobes, suggesting that visual processing was among the most computationally expensive activities their brains performed. The specific architecture of the bird visual system, the high density of photoreceptors in the retina, the large visual cortex relative to brain size, the presence of a specialized fovea for high acuity central vision, reflects the demands of high-speed three-dimensional aerial predation. A falcon stooping on prey is performing a computational task of extraordinary complexity, tracking a moving target, predicting its future position, adjusting flight trajectory in real time, while also managing airspeed, angle of attack, and the specific dynamics of a high-speed dive. The visual system that makes this possible is not a recent invention. Its foundations were laid in the Cretaceous, in the visual systems of the small, agile, three-dimensional predators that eventually gave rise to birds. The eye of Troodon, with its large size and forward placement, was performing similar tasks in the Cretaceous understory, tracking small prey through complex three-dimensional environments, predicting movement, guiding the body through the specific geometry of a predatory strike. The computational demands were similar to those of a modern hawk, and the visual system was probably similarly capable, differing in the details of its specific adaptations but similar in its overall architecture and emphasis. The bird eye and the dinosaur eye are the same eye in the deepest sense, the same evolutionary commitment to vision as the primary sense, the same investment in photoreceptor density and optic processing, the same architecture of depth perception through forward placement. The specific details differ between species and between lineages. The fundamental design is continuous. When a modern hawk circles above a field and fixes its gaze on a vole moving through the grass below, the hawk's visual acuity at that distance equivalent to seeing the newspaper headline from the far end of a football field, it is using an eye whose fundamental design was first established in a Mesozoic predator somewhere in the Triassic or early Jurassic. The eye of the hawk is the eye of the deep past, refined and specialized but recognizably continuous. You have eyes too, though their design reflects a different evolutionary history. The nocturnal mammalian heritage that traded color vision for low-light sensitivity, the subsequent re-expansion of color vision in the primate lineage as a specialization for fruit finding in the canopy. Your eyes are not hawk eyes, they are primate eyes, with their own specific history and their own specific capabilities. But behind your primate eyes, behind the specific adaptations of your lineage, there is the same ancient machinery, the same basic photoreceptor chemistry, using the same rhodopsin and conopsin molecules that have been the basis of vertebrate vision since the Devonian. The specific architecture of your visual system reflects the specific history of your lineage. The fundamental chemistry reflects something much older. Tonight your eyes are closed, or if they are open, they are not processing the visual world in the way they do when you are awake. The visual cortex is doing something else, participating in the dream state, processing internally generated imagery, doing whatever the dreaming brain does with the neural architecture that, in waking life, is used for seeing the world. The visual system does not rest when you sleep, it changes what it is doing. The hawk's visual system in the hawk's sleep is similarly redirected, not processing the field below, but processing whatever the sleeping hawk's brain produces. The dreaming hawk, with its extraordinary visual cortex, may have extraordinarily vivid visual dreams. We cannot know, but the architecture is there. And the architecture connects, through the evolutionary history of the visual system, all the way back to the first vertebrate eye, a simple photoreceptor structure in a Cambrian fish, capable of distinguishing light from dark, the beginning of the long elaboration that led through 500 million years of refinement to the hawk's fovea and the owl's enormous eyes, and the compound visual world of the bird that is sleeping right now somewhere near you. Close your eyes more completely if they are not already fully closed. Let the visual cortex do what it will. The world you have been seeing with your imagination tonight, the Cretaceous forests, the warm inland seas, the feathered predators in the Chinese forests, is held in the visual system even without external input, available to the dreaming brain if the dreaming brain wants it. The ancient world is available to you, it always has been, not as a visited place but as an imagined one, which is its own kind of reality, as real as a dream is real while it is happening. Let it be real tonight, one last time before the deeper sleep takes over. The feathers, iridescent, the water, warm, the bones, patient in their rock, the dark, old, and continuous and kind. Sleep well inside the ancient world, it has been waiting for you all evening. Let that be the last thought. Old light, ancient dark, the deep ground below, the ancient sky above, you resting in the middle of it, as everything rests, as everything has always rested. The insects are singing somewhere, as they sang in the Cretaceous. The world turns slowly, as it has turned for 4.5 billion years. The night continues its long, reliable course toward morning. You do not need to do anything. You do not need to go anywhere. You do not need to think about anything, or solve anything, or hold anything in your attention. The ancient machinery is running, the sleeping brain is working, the body is healing and consolidating and resting in the way it has been doing since long before any ancestor of yours was capable of worrying about anything. Sleep comes to you now the way it has always come, not summoned, not demanded, not forced. Simply available, in the quiet, in the dark, in the stillness that is the oldest condition of the living world. The Cretaceous night is very long, let it be. Good night. If you like this video, let me know where in the world you're watching from and what time it is. I'm always curious about that, and if you have a suggested topic, feel free to leave it in the comments. Thank you so much for watching. If you would like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one.